So guys, basically in this class, I'm going to talk about a very important concept, which is a building block for an entire generative AI ecosystem that we used to see. So it doesn't matter which model we are going to use, doesn't matter which platform we are going to use, but yes, a building block for this entire generative AI is basically RNN, then LSTM, then GRU, then encoder, then decoder, and then finally attention. So a self-attention based model or self-attention based concept. And this is something that we are going to revise. And after understanding this entire concept, believe me, you all will be able to understand an architecture of all the models which is available in this entire world till date, because more or less architecture of all of those models, or you can say a core architecture of all of these models or LLM models that we used to see nowadays a lot. And nowadays we are talking about this generative AI concept. So you all will be able to understand all of these things in a neat and clean way. So in today's discussion, I'm going to talk about, first of all, a story from a very, very beginning. And this story starts from a very basic concept, a very basic fundamentals called as RNN. And then LSTM comes into a picture, GRU comes into a picture, encoder decoder concept comes into a picture, and then there is a research paper called as Attention is All You Need, which has been published by Google in 2018, and that has changed the entire world of this Gen AI, you can say, and that was a beginning of this generative AI things. So one by one, let's try to unwrap each and everything, and let's try to understand the concept. Finally, I'll make sure that you all will be able to understand the complete Attention is All You Need research paper. So I'm going to open up a research paper. A step-by-step manner, I'm going to explain you a mathematical concept layer by layer. So what goes as an input, what comes as an output, how machine will be able to train itself, how machine will be able to learn itself. And then finally, I'm going to show you a GPT 3.5 or small GPT, nano GPT architecture. Believe me, you all will be able to correlate with each and everything. So shall we start, guys? Yes. And then GPT-4, obviously, which is having more than 96 plus self-attention kind of a layers into it. Yeah. So let's get started one by one. And again, so anyone and everyone who is going to ask you a question from architecture side. So these are the concept which is going to help you out in terms of answering all of those questions from an architecture side of any of these models. So first of all, let me share my screen and let me start talking about this entire concept one by one. So basically, we all are aware about a neural network. Now, neural network is nothing but it try to learn a pattern. So whatever data that we are going to give as an input, it will try to learn a pattern into a particular data set. And then eventually, once it will be able to learn a pattern with the help of feed forward network, and then in a backward propagation, it is going to adjust the weight, which is nothing but our relationship it is going to adjust. It is going to give us some sort of a output. Now, this is a whole purpose of creating a neural network. And this is what we try to study in our deep learning classes. Now, so one step forward. So there is a category called as computer vision. Now, inside a computer vision, we try to understand again a neural network, but a special kind of a neural network called as convolution neural network, CNN, which will be able to understand a pattern inside the images. And then based on that, you will be able to perform image classification. You will be able to do object detection, segmentation, tracking, and many more such kind of a task based on the image input. Now, so where this RNN comes into a picture and how this entire story has started. So guys, whenever we are trying to do a language translation, so I believe we all have used a Google Translator kind of a system at some point of a time, right? Or we all have used some sort of a chatbot, right? And nowadays we all are using this GPT based model, which is available on a various platforms. So obviously ChatGPT is one of the source, maybe a Cloud, maybe a Gemini, recently a DeepSeek. So again, there are so many such kind of a model which has been developed. So how this entire story has started and what was a problem statement in a beginning which people was or researcher was trying to solve. So when we talk about a simple neural network, so in case of a simple neural network, whenever we are trying to pass a data and then we are trying to get an output. So again, in a first iteration, let's suppose I have passed a data. So I have a simple neural network over here, right? This is how it looks like. Let's suppose, right? This is how it's been represented, at least inside a books, I would say, right? Inside a books. So let's suppose I have a neural network, and okay, let me create it by using a different color encoding. Okay. So in general, so this is how this basic neural network looks like, or maybe in our books. So this is how we try to represent this entire neural network. So where we'll be having an input layer, we'll be having basically a hidden layer. So this is going to be an input layer. This is going to be a hidden layer, and this is going to be a output layer. Now, let's suppose if I'm trying to do some sort of a prediction. So obviously I'm going to pass an input data. It is going to give me the output. In this particular place, it is going to give me the output. Okay. Now, so when I'm trying to pass a data again, let's suppose, so this entire network will not be having any kind of an idea that what I have done last time, because it is not trying to store, or it is not eligible enough to store a state of the data or a state of the entire operation that we have done in my past. So every time it is going to take a new data, and then it is going to generate a new output. And a previous, let's suppose at t-1, we are trying to do something, and at time t, we are trying to do something in terms of passing a data and trying to take out the output. Now, this model will not be able to retain a past memory. It will not be able to understand that what we have done in my past. And obviously, if it is not able to retain something as a memory, if it will not be able to understand that what I have done in my past, it will not be able to establish a correlation between a past event and a current event. Now, so in this situation, it will not be able to solve any such kind of a problem which depends upon the previous time. For example, so I'm trying to use a lot of statement over here. I'm trying to generate a lots of lines over here, but each and every next line which I'm trying to generate while giving a lecture, right? Let's suppose if I'm trying to give you a lecture, which I'm trying to give a lecture, obviously, right? So let's suppose if I'm trying to give you a lecture, and every time, so whenever I'm trying to generate a new line or a new word or a new sentence from me, so obviously this entire new line, new word or new sentence depends upon the previous sentence which I have already said. And this is how you all are able to correlate. This is how you are able to attend a lecture. You all are able to understand a concept which I'm trying to explain. So let's suppose I'm a network, I'm a neural network, and practically, yes, I am basically a human based neural network. So basically I'm trying to do each and everything over here, and which is having a dependency with the past. But this particular neural network which I'm trying to show you, or that we try to study in a very beginning in a deep learning classes, so this neural network will not be having a capacity to hold any kind of a state or to hold any kind of a past event. So it will not be able to behave the way I'm trying to behave as of now. But if I'll talk about NLP, a natural language processing, so where we try to deal with a text, where we try to deal with all the sentences or phrases or maybe a paragraph. So obviously over there, this requirement is very much needed, or this problem statement must be solved so that whenever I'm trying to generate a new data, it should always be able to correlate with my past data, and based on that, it should be able to give an answer. Now, this is where the concept of this RNN, a new kind of a neural network people have started developing, which is called as basically a recurrent neural network, where so people was trying to maintain that, okay, so this kind of a network must be able to understand something which has happened in a past, and whenever it is trying to generate a new data, whenever it is trying to give me a new output, it should always consider a previous output, and then based on that, maybe some sort of a factor of the previous outcome it is supposed to consider, and then only it is supposed to give me the next output. And this is where the concept of a recurrent neural network comes into a picture. So I hope all of us are able to understand that why we are talking about a neural network, and this concept is, or this phenomena is very much crucial, very much important to solve any kind of a NLP problem that we try to solve. Maybe a speech recognition, maybe a text generation, maybe a machine translation, maybe a time series kind of forecasting, maybe a sentiment analysis, right? For each and everything to solve all of these problems, speech recognition, text generation, machine translation, time series forecasting, sentiment analysis, we need such kind of a network. And this is where the concept of this entire recurrent neural network comes into a picture, where people said that okay, so whenever system will try to provide some sort of an outcome, whenever system will try to generate, or neural network will try to generate something new, what I will do is, so maybe I'll try to store something from a past, and then that something from the past I'm going to attach with the input, and then it is going to give me the new output. So they have proposed that okay, so what if we can try to create a neural network over here, right? We can try to create a neural network over here. So where we can try to give a input, that's completely fine. So x1, x2, maybe x3 over here, maybe x4 over here, and then there is something called as h, and h. So h at t minus 1, h at t minus 1, h at t minus 1. So maybe a multiple input. That's the reason. So I'm trying to take a multiple neurons. Otherwise, you can try to take single neurons as well. And then there will be a hidden layer in between, and then there will be the output layer. So here, I'm not just trying to provide a new input, but I'm trying to provide something which I was able to receive from a past. So let's suppose this entire neural network is trying to give me this as an output. Now, when I'm trying to predict something new, when I'm trying to estimate something new, so what I will do is I'll try to provide this entire information attached with the input or new input, for which I'm trying to do a prediction, and it is going to learn accordingly, and it is going to give me the entire output. So I'm not drawing all the arrows over here. I'm just trying to draw rough kind of an arrow so that you all will be able to understand. So this is where the concept of a recurrent neural network comes into a picture. So where instead of passing a complete new data, I'll try to pass even a past data, or even a past instances, or the past outcome, so that my system will be able to remember each and everything. Now here, so if mathematically, if I have to write this entire things, so here you can try to write it down mathematically, maybe in this way. So let's suppose if I'm trying to do some sort of a prediction over here. So this is nothing but this entire output which I'm trying to predict over here. So this is nothing but it is going to be a function of weight h t minus 1 plus weight of x, a new input, xt plus b. Now, what does this represent? So obviously there will be some sort of a function over here, which is going to do some sort of a classification, or maybe it is going to help you out in terms of giving you the output. So this is the function which I'm trying to attach, and this is the data input which will go. Now this data says that I'm trying to take a weight. So weight is this, right? I'm trying to take a weight, or maybe you can try to consider this one. So this is a weight which I'm trying to pass. I'm trying to multiply a data at ht minus 1. So ht minus 1, whatever I'm trying to provide, plus I'm trying to pass a new data. So wx into xt. So weight, let's suppose this is a wx, or maybe this is the wx, anything I can try to consider layer by layer. So I'm trying to provide a data x, and then I'm trying to multiply this wx with this, plus I'm trying to add some sort of a biases over here. And then this is going to give me the final output, which is called as ht. Just a mathematical representation. Now this function could be anything, this function could be anything. We can try to take any kind of a function inside the hidden layer, and then on our output layer, so accordingly what kind of a task that we are trying to perform, so we can try to take a function over here, and this is going to be the input. But yes, this is going to be the final function mathematically. So where if I'll talk about this function f, so f is nothing but my activation function in general. ACTIVATION activation function. So maybe we can try to take activation function as a sigmoid function. We can try to take activation function as a tanh function. We can try to take activation function as a ReLU function, a leaky ReLU function, maybe a Swiss function I can try to take as a activation function. And this whole data, right? This whole data will be passed inside that particular function. And this is how we try to build a neural network in general, right? This is how we try to build a neural network at the end of the day. So fine. This is something that people have developed as a part of a recurrent neural network, which was a small changes from a actual neural network that we try to study in a beginning of any deep learning concept. Making sense, guys, to all of us? So how people have started designing this recurrent neural network and how this recurrent neural network is different from the neural network that we try to study on in a beginning. Yes? Everyone? Yeah. So this was the core phenomena behind a recurrent neural network. So where we try to pass a data along with the data. So we try to pass a previous output and then that behaves as a total data. So apart from my actual data, so we are trying to add more data, or you can say some sort of additional data over here, which I'm getting in a past from the previous outcome, whatever data which I have received, so that system will be able to understand that what I have done in a past, like I said. So whatever new line which I'm trying to generate as of now, so obviously it depends upon my past. So I'm trying to pass this previous line into the existing one, and then I'm trying to generate the new lines. So this is what it is going to do. Now, so again, people have started facing a problem with respect to this kind of a recurrent neural network. So what kind of a problem that people have started facing? The problem number one that people have started facing is something called as vanishing gradient problem. VANISHING, vanishing gradient problem. Or you can say a second problem is exploding gradient problem. So these are the two problems that people have started facing out of this entire network. And it was a small modification from the actual neural network that we try to study. So the very first problem is a vanishing gradient problem. The second problem is a exploding gradient problem. So anyone, guys, who is having idea about a vanishing gradient problem, exploding gradient problem? Because I believe this two concept, vanishing gradient and exploding gradient, is a part of our core neural network fundamentals as well, right? So anyone who is having idea about it? Yep, anyone? So Dev Kumar is saying yes. So I believe this phenomena is nothing new for us. So I believe we all try to encounter this kind of a vanishing gradient problem concept and exploding gradient problem concept in a neural network as well, almost in a all neural network. So Rohan is saying that when weights goes to zero, vanishing gradient, and Rohan is saying when it goes to infinity, it's called as exploding gradient. Okay, okay. So vanishing gradient is nothing but, so when gradient start shrinking exponentially, and in that situation, it is very difficult for any kind of a model to learn or to retain a long sequences. And I believe we all understand that how training happens in a backward propagation. So in a backward propagation, obviously we try to find out what? We try to find out a loss. So loss is nothing but a difference between expected outcome and the predicted outcome. So let's suppose this is my expected and let's suppose this is my predicted. So we try to find out a loss and then we try to use an optimizer, and what optimizer is going to do. So maybe a SGD optimizer we try to use, a stochastic gradient descent optimizer, or maybe Adam optimizer. We try to pass a loss over here, and then this gradient optimizer will do what? So it will try to change all the weights, and this is how learning happens, right? So learning happens with respect to our weights, because whatever activation function or maybe output function that we have given over here, so this is going to be the constant, right? This is going to be the constant layer by layer. Actual learning happens. And what is the meaning of actual learning? The meaning of actual learning for any kind of a neural network, or even in machine learning, if I'll talk about it. So meaning of learning is optimizing or maybe finding out a new relation. And how I will be able to find out a new relation? By changing all of these weights which is available inside all of these connections. Then only we say that okay, so my model is been trained and my model is able to give maybe a 90% accuracy, maybe 99% accuracy. And all of these happens in a backward propagation. Basically, we try to estimate a new weight, and we keep on doing it unless and until we are not able to build a stable model. Simply means that my loss will stop decreasing or increasing, and I will be able to get justified accuracy from the particular model. Means difference between expected and the predicted one will be as less as possible. Now that depends upon the data, depends upon the network architecture, depends upon the problem that we are trying to solve. But yes, this is the meaning of a training in general. So when we say I'm trying to train the model, so obviously I'll try to pass a data, that is something called as feed forward, right? So in a forward direction, I'm going to pass a data. It is going to calculate, multiply a data with the weight, plus it will try to add the bias. It will try to pass it inside this activation functions, and then same thing it will keep on doing. And then on an output layer, it is going to give me the output. That is something called as Y prediction. I will try to calculate a loss. I'll try to pass a loss into one of the optimizer. The famous one is SGD or maybe an Adam optimizer. And then that optimizer will help me out. And I believe we all are aware about a chain rule. If you are not aware about chain rule, so recently in my machine learning class, FSDS data science class, I have already talked about it, and that too with respect to a complete derivation by taking a numerical calculation for each and every step, that how this actual calculation happens. And I have not just done the derivation over there. Yeah, derivation was a part of it, but apart from that, so I have taken a numerical table, a numerical data, and based on that, how weight is going to change. So how W new is going to be W old plus minus eta, which is a learning rate, and then like a partial derivative of a loss with respect to the weight. So this is something that we have already calculated in that particular class. So if you would like to get into a detail of it, if you are not able to recall the concept, or maybe if you're not able to if you're not even aware about those concepts, so please you can go and revisit those classes, so that it will give you the whole idea that how training actually happens. But yeah, so anyone and everyone who is aware about a neural network training, so we all understand this entire part at least, and this is my expectation, at least inside this interview preparation session, that we all understand a basic phenomena and understanding about the entire neural network. So here I was talking about a vanishing gradient problem, that the basic RNN structure which I'm trying to show you, it was having a vanishing gradient problem. It simply means that it will not be able to train itself for a very, very long sequence of the data. Let's suppose if I'm trying to take a data which is having thousands of words, it will not be able to retain, it will not be able to remember from the past, or it will not be able to adjust a weight accordingly. And if I'll talk about exploding gradient problem, so in that case, the gradient will be very, very high. It simply means that it is going to make a big changes, and if it is going to make a big changes instantly, again eventually I will not be able to learn. It simply means that I will not be able to find out a combination of a perfect weight. So that was a problem that people was facing. Now, so once they were facing this kind of a problem, so they came up with a new idea, that what if we can try to modify this entire network a little bit, right? This entire network a little bit. What if we can think about a new architecture which will be able to store a long sequence of a data, which will be able to build a memory inside it, which will be able to understand things for maybe things in a better way with respect to sequences of the data, whatever we are going to pass. And this is where, right after RNN, so they have started deriving a new concept, which is again coming from RNN itself, called as LSTM, long short term memory. This is what it means. So long short term memory, just to solve these two problems, so that I will be able to understand, I will be able to learn even from a long sequence of the data. And this is where concept of LSTM comes into a picture right after RNN. So where they have designed three different kind of gates inside a neural network. Again, gates are nothing but just a combination of a neural network itself, right? So again, whatever picture that you have seen over a internet with respect to a LSTM. So all of those components or all of those gates are technically a neural network. This is how we have built the gate. So whatever neural network that we are talking about over here, so those gates are nothing but a neural network. So let's talk about LSTM and let's see that how it is going to solve a problem which has been created by RNN, recurrent neural network, or vanilla recurrent neural network. Shall we go ahead, guys? Shall we talk about LSTM? So I hope we all are able to understand so far that what was a problem with the conventional neural network, then why we are coming up with the recurrent neural network, what was a need of it, and then what was a problem with the recurrent neural network, and then why we are coming up with the LSTM. Now let's try to understand that how LSTM is going to solve a problem, basically, right? So how LSTM is going to solve a particular problem and how it is going to give me the solution. Let's try to understand in a step-by-step manner. Because yes, if I have to do some sort of a natural language processing, if I have to do a speech recognition, if I have to do a machine translation, just like a Google Translate, or if I'm trying to solve a time series based problem, I need a stable model. So I have to look for a different kind of a solution. Fine, guys? Okay. So let's try to talk about LSTM. So again, I'm going to draw an architecture over here. So the architecture that we generally see over the internet, but I'm going to explain you even with respect to a neural network. So here, again, the problem statement was same. So people have started designing a kind of a network. So let me draw this network. So here inside this network, again, you will be able to see two input. One is a current input, which I'm labeling as a XT, and one input from T minus 1, means from a previous output we are trying to give as an input, because that was a core fundamental. That was a core fundamental with respect to any kind of that with respect to a RNN. So here inside a LSTM, which is called as long short-term memory, there will be two input. One is a current input and one is a previous output, which will go inside the entire network. And then on top of that, you will be able to see that here is a sigmoid function, and then it is going to give me some sort of a output called as FT. I'm going to explain you that what is the meaning of this FT. There is a dot product over here. Then there is a memory channel, you can say T minus 1. I will try to explain you that what is the meaning of this T minus 1 and how this calculation happens. Everything I'm going to explain you in this particular class itself. So this is one of the gate. Then there is another gate that you all will be able to find out, and this gate, let me use a different color coding over here. So there is one gate, and then there was another gate over here. Again, I'm not good with the diagrams. My handwriting is worse, I would say, but yeah. Tan H. And here, so tan H is going to give me some sort of a output. We are going to multiply it with this particular output that we are going to get. And then in a memory channel, I'm going to perform addition operation. So this is basically a addition operation, which I'm going to perform over here. And then let me use a green color over here for a third gate. So here, again, this will go, this will give me basically an output, and this will be multiplied with data coming from a memory channel, hypertangent, multiply, and then try to build a memory at T. This is going to give me HT. So this is a network which is called as LSTM network. How many of you are how many of you understand this network, guys? Anyone? So in a chat, please. How many of you understand all of these three gates which I have written over here? So what this gate does actually, and how it will be able to give you the output, how it will be able to retain a memory from a past. Any idea, guys? Anyone? Yes? Any idea? Okay, so Amrindra is saying yes, Rohan is saying yes. Okay, so we have a couple of people who understand this particular network. Okay, so those who don't understand this particular network, let me explain you, or maybe we are not able to recall it because yeah, if you are uh, going through these kind of a network after a very, very long time, so for sure you will not be able to understand it. Maybe you are able to remember the diagram, but yeah, it's very difficult sometimes, even for me. So whenever I have to come for the class, so obviously I make sure that I revise the concept and then I come to the class so that I will be able to explain you with the fresh concept, because obviously this kind of a network is not easy to remember. Sir just applied a code in LSTM, didn't go through the architecture much. Okay, not an issue, Kripa, but yeah, coding is very easy. It's just like calling one single function and then your coding will be done. Layer by layer, you will be able to build the things. But in an interview, people are going to ask you a question from an architecture. So let's try to understand this particular part, guys. So here, there is something called as CT, right? Now, what is the meaning of this particular CT? So basically, it's called as cell state, right? This is called as cell state. Now, there is something called as FT. So this is nothing but it's called as forget gate, FOR, forget gate. This FT is called as basically forget gate. And then there is something called as IT. So let me draw the IT wala part. So here, this is something called as, sorry. So this is called as IT. So this IT, so what is this IT by the way? So IT is nothing but basically it's called as input gate over here. And then we'll be having a OT. So this OT is nothing but it's called as output gate. So this is basically a forget gate. We have basically a cell state at t-1 we have over here, and cell state at time t we have over here. There is something called as output gate that we have. There is something called as input gate that we have. Now, the entire story of this entire LSTM starts from this and this component. Input from a past t-1 and input from a present. For example, so in this particular network, I was trying to give a current input and then I was trying to give an input from the past in a similar manner, right? Just try to understand these things as a neural network, that we are trying to pass a data into a neural network, and I can decide that how many hidden rails will be there, how many input tokens will go, or maybe a words will go, or maybe a vectors will go, and then I'll try to decide that okay, what is going to be the output function. So here we are trying to give a input. Now here, once we are trying to give an input, what will happen to those inputs? So now those input will go through all of these three gates, and this is going to give you a superpower where you will be able to remember, your network technically will be able to remember that what I have done in a past, and then when I'm trying to produce a new data or the new output, so what kind of a output I'm supposed to produce. This is something that you will be able to understand out of this one. Now, one by one, let's try to understand this entire phenomena. So first of all, let's try to talk about this very first gate. The very first gate is what? This is a forget gate that we are talking about. Now, what this forget gate does and what kind of a input or what kind of a output it is going to give. So obviously input wise, this forget gate is going to take these two input, a data from past and the current data this forget gate is going to take. Now, what this forget gate will be holding after this particular step. So what it will be holding at this point of a time here. So what it will be holding. So obviously these two inputs will go inside this sigmoid function, which is a part of your neural network. It will go over here, and then whatever output it is going to give you, so that will be a part of your forget gate. And then we'll try to understand so why this gate is necessary, why this gate is important inside my entire LSTM network. So here, this roles and responsibility of forget gate is to determine that how much of the previous memory we have to forget, how much of the previous memory we have to retain. This is the responsibility of my forget gate that you are able to see. So responsibility is very simple, that how much we are supposed to remember and how much we are supposed to forget. As its name suggests, forget gate. So let's suppose if I have a sentence with 100 words, maybe I have to retain only a couple of words out of it just to understand the past sentiment, right? Just to understand the past sentiment. For example, if you are reading a books, even as a human, so when you are trying to read a books, so it's not like we try to focus on every word that we try to read out. Yes, intentionally, if you will try to focus, so you will be able to know that I'm not focusing on each and every word, but still I'm able to understand a summary of a particular line or summary of a particular paragraph. Yes, guys. And then when you try to read the next paragraph, you all will be able to correlate with it. Can I say that even we as a human does the same thing? It's not like word by word or punctuation by punctuation, you will be able to remember each and everything, parts of a speech to parts of a speech. You will be able to remember each and everything, and then you will try to understand the next paragraph or next sentences. No. So we try to retain just a set of a understanding from the past, and then based on that we try to build a current understanding. Now this is where in case of LSTM comes into a picture, where forget get inside this LSTM will help you out that okay, how much data you are supposed to retain and how much data you are supposed to forget. Now if I'll talk about this forget get output, so means what will be holding at this point of a time. So maybe I can try to write in this way, forget get. So here we have a sigmoid function in this particular place. So obviously sigmoid function, and then we are trying to pass these two inputs, right? These two inputs. So what we can do is, so we can try to multiply this with the weights. So weights for the forget gate, and then we can try to say that input wise ht minus 1 and xt will go plus biases. So generalization wise, I can try to write this entire equation for a forget gate in this particular way. Now, what is the meaning of this W and then H and then T? It's nothing but I'm trying to call this kind of a neural network over here. That okay, so there is a input. So input is a combination of my current input and my past, plus there is this kind of a layer that I have already drawn over here, which will be having a weights. So I'm just trying to multiply weight with the previous input and the current input, plus I'm trying to add some biases. So technically here I'm trying to say that I'm talking about a neural network, right? So here we'll be having this kind of a architecture, this kind of a layer in place of this gate. And again, so this gate is going to give me this kind of a output. So summary wise, I have written this entire function in this particular way. So this is what this forget gate is going to do. So from a previous learning. Now everything is a learnable parameter. So when I'm talking about this weight, so obviously weight is what? Why we are trying to introduce a weight over here? Because it's a learnable parameter. So system is going to learn, even your network is going to learn with respect to a weights, so that it will be able to understand that okay, how much we have to retain and how much we have to move it forward. This is the reason. So we have introduced a weight component over here, because weight component is the only component which is going to help you out to build the relation. So this is the responsibility of this particular gate. Now, so let's talk about a next gate over here, which is basically a input gate. Yeah, which is basically a input gate IT. So now what this input gate is going to take. So as you can see that this previous input, right? This previous input is coming over here and the current input is also coming over here. The previous input and the current input is flowing through the entire region, So even over here, I will be having this particular input, a past one, and I will be having a current one. We have a sigmoid over here. So which is nothing but my activation function, I can say. So IT is nothing but if I have to write IT, so and this is going to represent a neural network. So we have one neural network. Again, we have a second neural network over here, and I can try to write it down again in the same way. So wait for a input gate, and then ht minus 1 and xt plus biases. Simple. So this is what you will be able to get over here as a IT, as a input gate output. Okay, that's completely fine. We are able to understand this particular part. Now coming to the next one. So here, right? So here we are trying to perform some sort of a addition operation. As you can see that inside a network, we are trying to perform some sort of a addition operation, and we have a cell state running through this entire line. So we have a previous cell state over here, and then every time, so we are trying to generate a new cell state over here. So what cell state actually does? So cell state is going to combine a forget gate and a input gate. This is what this entire line is trying to do. As you can see, there is a plus symbol over here, and here we have basically a multiplication symbol, or you can say a dot product. So whenever you will try to find out a new forget values, it is going to multiply with the previous cell state, and now this will flow over here. Now we have a cell state t minus 1 into, which is a dot product. So cell state t minus 1 dot of forget output. So this will come in this particular place, and then input, right? So input gate will come over here. We are going to perform a multiplication operation, then we are going to perform the addition operation, and we are going to update our cell state in this particular place. And responsibility of cell state is very simple. So it is going to combine a forget gate and a input gate, and it is going to update the memory, because this cell state is responsible for memorizing things, and it will throughout. That's the reason. So we have this line throughout the entire network, so that it will be able to memorize, and it will make that memory available throughout the computation. Doesn't matter whether we are doing computation over here, or maybe here, or maybe here. So in each and every computation, cell state is going to contribute, and technically cell state is nothing but my past memory that I have built, and then the new memory that I'm trying to build. So how this cell state computation is going to happen, by the way. So input, obviously we have over here. Then you must be able to see that the same input is going through a hypertangent function as well, right? And it's coming over here, hypertangent function, and then it's coming over here. And then we are trying to multiply IT, which is nothing but my input get output. And then this hypertangent output we are trying to multiply. So let's suppose I'm going to mark this one as a cell state at time t delta. Okay, I'm going to mark that as this one. So cell state t as delta is nothing but it's a tanh, so hypertangent, and then same data will go, right? So same data will go. So wait for a cell state ht minus 1 xt plus b. So same thing will go over here, and this is going to build my intermediate cell state. Now if I'm going to multiply input into this delta of cell state, then I will be able to get output over here, and then whatever output which I'm going to get from here and then here, I'm going to multiply it. So this entire outcome is nothing but c t minus 1 dot of forget gate plus symbol we have, plus we have it into c delta of t. Now if we are going to combine this entire component, it is going to build my final cell state value. Simple. It is going to build my entire memory. So when I'm trying to talk about a memory, so again, just try to focus over here. So my memory component is nothing but it's a combination of a previous memory, which is ct minus 1, the memory that I have built. Then it's a combination of a forget. So how much data we have to forget, how much data we have to retain based on the current input. Again, so we have a I component, IT component over here, which is nothing but the current input that we have given over here. And based on that, we are trying to take the output plus a delta 1. Right? Plus a delta 1 over here. So now if you're going to combine this entire thing, this is going to build my memory. Or even as a human being, when we try to retain something in my memory, so obviously these are the kind of a component mathematically, if I'll talk about. So all of these are component which comes into a picture, which will help me out to memorize something at the end of the day. So this is how we will be able to build a final cell state. Now coming here. So let's suppose we are talking about the output in this particular place. So here, how I will be able to calculate the output. Let's try to talk about that particular part. So again, we have an output and we have a neural network over here. And this HT and XT is running throughout the entire network. It's available throughout the entire neural network. Means it's available here, 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 and here. So if I'll have to write the output over here, so let's suppose if I'm writing maybe a OT, which is nothing but an output. So output is nothing but sigmoid. And then inside that, wait for the output, means for the neural network, wait, it will go over there. Then ht minus 1, and then xt plus b plus biases. Now this is going to build my output. So again, like I said, so here I will be having a neural network. And here, if I have to find out a next hidden state, which is nothing but HT. HT is nothing but a hidden state, obviously. So if I have to find out a next hidden state, so next hidden state is nothing but this output. So this component is going to be nothing but HT is going to be nothing but this OT output. Then here we have a multiplication. So multiplication, and then tanh, and from here, so we are getting what? We are getting a CT, cell state we are getting. So this is going to give me my hidden state, which will be propagated to the again next layer, right? Which will be propagated to the next layer. So that it will be available for the next time. So this ht minus 1 will be available. Now this ht is nothing but it's a combination of what? The output that I have received last time. Yes, it's a combination of what? The output that I have received and whatever memory that we were able to build. Now this component is important to retain any kind of a data or to understand any kind of a things or phenomena that my neural network has gone through in my past, because this HT is a combination of my current output as well as it's a combination of my cell state, which is technically a memory. And eventually my cell state depends upon my previous cell state, my previous memory, plus how much data we have to forget, plus the input, plus hypertangent of the input, multiplication of it, right? So everything is connected. And finally, this will become my ht minus 1 in my next lap, in my next iteration. And this is how it will be able to remember. So this is having all the component which is actually required for memorization and to understand my entire past. And this is how this entire LSTM network works. So technically there are a 3 gate you will be able to find out. So one is a forget gate, one is an input gate, and one is a cell state that we try to build. Obviously we have an output gate. So gate wise we are trying to build 3 gates. Component wise we have 4 component, major component. So one is a forget gate, input gate, and output gate. Component wise we have input, output, forget, and we have a cell state. And this is how this entire network will be built. We have in general 3 full-fledged neural network in all of these gates that we are talking about. So we have a neural network with its own weight inside a forget gate. We have our own neural network with respect with its own weight inside our input gate. We have our own neural network with respect to its own weight inside the output gate, and everywhere training is going to happen. So even over here it is going to learn in a backward propagation, even over here it is going to learn in a backward propagation, and even over here it is going to learn into a backward propagation. And what is the meaning of learning? Learning means we are trying to optimize all of these weights. That's it. This is the meaning of it. So that I will be able to learn how much I have to forget. I will be able to learn so what will go as an input. I will be able to learn that what will go as a output finally. Is it making sense to all of us, guys? Yes? Is it making sense to all of us? Yes. Okay. So I believe this is a good revision for all of you. So I'm just going through a revision, guys. So I'm not, because in general, when I talk about this kind of architecture in my classes, so I spend more and more time. But here, so as we are preparing for the interview, so like I said, even in a chat that we'll be talking about the revision over here. Otherwise, I generally take 1.5 hour, 1 hour of, well, not 1 hour, I would say 1.5 hour time just to show you the entire derivation and to make you understand that, okay, fine. So this is how this entire network works. But yeah, I believe for revision, this is more than enough. Fine. So here, this is the LSTM architecture and this is how it is going to work in general, and hope you all will be able to recall it. Now, where and for what purposes I will be able to use this entire LSTM? So LSTM use. So where I will be able to use this entire LSTM. So obviously I will be able to use LSTM for a sentiment analysis for a very, very long sentence. I will be able to use this LSTM for a machine translation. So obviously machine translation means Hindi to English, English to Punjabi, or maybe Hindi to or English to French, or maybe a German. So whatever Google Translator is able to do. So obviously I can try to do it. And even in my class, so what I do is that whenever I talk about a LSTM, so I try to take one data and obviously a label data. So where I will be having an input as well as output. And in my live class itself, I try to show them that, okay, so this is how this entire LSTM is going to work, and see, we are able to do a translation. So this is practically possible. This is practically possible on a smaller scale. You will be able to pass a input data and then you will be able to translate your own data in some other languages. Depends upon your data preparation and depends upon the network that you are going to build. But yeah, like I said, so I take more and more time. So when I talk about the same architecture and the implementation of it in my live classes, because obviously in my live classes, so people will not be aware about any of these things. So if people are completely zero about any of these things, so I have to go from ABCD of it. So if some of you are not aware about these things, and if you would like to understand these things from a zero, come to my FSDS class, and I believe all of you must be having a class, FSDS class access. As of now, I'm talking about machine learning. After that, I'll be talking about a deep learning, then computer vision, and then NLP. And inside NLP, all of these concepts in a very, very deep and very, very detailed. Obviously, I will be able to build a chatbot, so which will be able to understand the context. So context-based chatbot, if I have to build, so I will be able to build it, chatbot. Now, which will be able to understand something from the past, and then it will be able to give you some sort of an answer. Now, I will be able to build something like a stock market prediction system. Because it is going to be the time series problem, and time series problem requires a long-term memorization. So this network is best for a time series one, even for a weather forecasting, because weather forecasting is again falls under a time series problem. Or maybe a Siri or Alexa kind of a system I will be able to build. And many more things I will be able to build on top of this one. Okay. Now, so people were able to build this entire LSTM architecture, and obviously this architecture was performing better than the previous vanilla RNN architecture. This is called as vanilla RNN architecture, where we were not trying to take care of a memory or any long sequences. So where we were just trying to pass a previous output into the next one. That's it, which we were trying to call as a HT-1, or previous hidden state into the next one, which we were trying to call as a HT-1. Now, so here, we were able to build a LSTM, but again, there was a certain problem with the LSTM. Obviously, vanishing gradient problem or exploding gradient problem, till a particular stage, we were able to solve. But we were not able to solve these things completely. Plus, we were having a 3 gates over here. So again, in every gate, we are having a neural network. So number of neural network has increased. And if number of neural network has increased in all of these gates, so in this entire architecture, obviously this model is going to be complex as compared to the previous one, because here we will be having just a one single neural network, but here, so we are talking about a combination of a neural network, a multiple neural network, and technically a 3 neural network we are talking about in one single system. Now, so if that is a case, then people have came up with again another kind of architecture to solve this complexity problem, and that is something called as GRU. So people have named it as a gated recurrent unit neural network. So GRUNN basically. So gated recurrent unit people have designed, so which is nothing but an extension of an LSTM. So where it is trying to solve the complexity problem of the model. So instead of handling multiple gates or maybe a 3 gates, maybe I can try to reduce this entire architecture into 2 gates. But more or less, even GRU is going to do the exact same thing. But yes, it will be way faster as compared to your LSTM that we have designed over here. So now let's talk about a GRU, a gated recurrent unit system, and how basically it's been done and how it is going to basically work. Like I said, so obviously gated recurrent unit system is way faster as compared to LSTM, because we were trying to reduce a number of gate inside a LSTM, and then we came up with the GRU. So one by one, let's try to understand that how GRU architecture looks like and how it is going to behave, how it is going to work. So inside a GRU, instead of finding 2 gates, you will be able to find out only, so inside a GRU, instead of finding 3 gates, you will be able to find out only 2 gates inside a GRU. So how does that looks like? Let's try to understand. So here, again, I'm going to draw the architecture diagram of it. So let's suppose this is my layer and I can name it as HT-1. And then there is a it's a bit tricky to design this layer. So let's suppose if I'm going to pass my input xt, so again same kind of an input, one input from a past hidden state t minus 1 and one is a new input xt at time t we are trying to pass over here. Now how it is going to behave and how it is going to work, let's try to understand. So here, let's suppose this is my input point. So here I'm able to get the input. Now it will go inside a very first neural network, and here I will be having a sigmoid function, and then it will go inside a second neural network, and then again we'll be having a sigmoid function over here, and then it is going to do some sort of a math, and then finally it is going to give me some sort of a output. Now let's try to talk about that particular part. So here we have one passive line, and from here, so let me draw so that it will be visible to all of us. Like I said, this design is a little bit difficult as compared to the previous one that was very much straightforward. And we are trying to extend this entire line even till this particular point, so where it is going to meet my hypertangent. So this is one of the gate. Now if I'll talk about this particular gate, multiplication, and then there will be a hypertangent over here, and this is going to give me basically a delta of h. Now it is going to combine here, and we'll be having addition operation. Now this is going to build my h of t in general, and then here, so this gate will come, it will try to perform some sort of a minus operation, and then it will go here, it is going to multiply. Now if I'll talk about this particular one, so this will be combined with this one, and here this is how it is going to flow. So flow is going to be this and this flow, and we are going to connect this hypertangent with the input. So maybe I can try to draw this line. So here, this is something called as GRU architecture. Now in this particular architecture, you will be able to encounter only two kind of a gate. So one is basically this particular gate. So this particular gate, and one is basically this particular gate. And it is nothing but people have collapsed the previous gate, which was a 3 gate available inside a LSTM, and they have designed basically 2 gate out of it. So one gate is called as update gate, and then other gate is called as basically a reset gate. So let's try to understand. So what is a update gate and what is a reset gate? So here, this gate is called as, this entire gate is called as reset gate. Now if I'll talk about this particular gate, so this is called as update gate. Now what it is going to take as an input and what it is going to take as an output, let's try to understand that particular part. So if I'll talk about maybe a update gate, so as you can see that update gate is trying to take input from the past. So this is my past input, past hidden state, and this is my new input. Now both of this line coming inside this one, right? Both of this line is coming inside this one. So this update gate will be responsible for updating a memory, or it will be able to control that how much of the previous state should be carried forward. This is what this update gate is going to perform, that how much we are supposed to carry forward from my past, or whatever that I have learned, or whatever that I remember, or whatever which I am able to memorize. So how much I am supposed to pass to the next one. This is something which will be like a update gate will be responsible. So here, if I'm going to write down in terms of a function, so let's suppose if I'm writing this update gate as a z, so z of t. So your z of t is nothing but it's going to be a sigmoid. So as we have a sigmoid over here, as you can see, so it's going to be the sigmoid, and then wait for, you can say, a z, the gate that we are talking about, or update gate that we are talking about, and then h t minus 1. So obviously which is coming from here, it's combining here, and then x of t, a new input data, this one, plus a biases for this particular layer. So wait of this one. So This gate will be responsible for retaining a state from the previous one. Simple. And it is going to use basically a sigmoid function. Now, if I'll talk about this reset gate, this particular gate, so as you can see that inside a reset gate, so we are trying to pass a data, plus we are trying to perform some sort of a multiplication over here. So if I'll talk about a reset gate, just a reset gate, so maybe I can try to write a function in this way. So reset gate function at time t is going to be a sigmoid. So technically I'm writing for this output. So here, let's suppose if I'm able to get RT as an output. So it's nothing but sigmoid of this weight of the reset and then ht minus 1, so previous hidden state, and then a new data plus biases for basically this particular reset gate. So this is going to get output over here eventually. Okay, now so here this reset gate is going to determine that how much past information we are supposed to forget. Simple. Reset gate means it will be able to determine that how much past information we are supposed to forget. And it was a roles and responsibility of this forget gate in case of a LSTM. Okay. And almost it was behaving in the exact similar way. So we were having a previous input that we were able to pass inside my sigmoid function, and I was able to get ft. So which is nothing but my forget gate output I was able to get. So here reset gate is going to behave more or less in the exact similar way. Whereas my update gate is going to control that how much of the previous state should be carried forward. Means one will help me to forget and one will help me to carry forward a information that, okay, how much information I should leave, how much information we are supposed to carry forward over here. Now, here you must be able to see this one, which is called as HT. So it's called as basically new memory builder, or this HT is nothing but my memory line. So this is helping me out. This hidden state is helping me out to retain a new memory. Now here, so you will be able to see that this HT that I'm talking about in this particular place, or maybe HT that I'm talking about in this particular place. So it's nothing but coming from, right? It's coming from basically this entire reset gate, as well as somewhere it is trying to combine, or it is trying to perform some sort of an addition operation with respect to my update gate as well. Because reset gate will flow through this one. Obviously, it will try to do the multiplication with my current input as I have already connected. So here I will be having RT into my current input, which will flow through this one. And here, so I'm going to perform the multiplication operation of whatever input which I'm receiving from here. And then here I'm trying to perform the addition operation. So addition operation of what? So whatever data which I'm able to receive from the update gate. So I'm just trying to perform the addition operation. And then after multiplication with a tangent. So after multiplication with the hypertangent, and tangent is going to take my current input, I'm trying to create my new HT, or here I'm trying to create my H delta D. And then I'm trying to just multiply. So here H delta T if I have to write, H delta T if I have to write, so I can maybe write in this way. So hypertangent, and then wait for this H, H T minus 1, same story, and XT. But here, so when I'm trying to write wait T minus 1, so maybe I can try to multiply RT as well, plus B of H. So this is something that I will be able to receive in this particular place. As we can see, there is a multiplication, right? There is a multiplication over here. So this is something I will be able to retain. Now, if I'll talk about a final HT, which is helping me out to update a new memory. So it's nothing but 1 minus. As you can see, there is a symbol called as 1 minus over here, 1 minus. So here it's nothing but 1 minus Z of T. Now my Z is nothing but my update gate output, as we have already written. So 1 minus Z of T into H of T minus 1 plus Z of T into HT delta. So this is going to create a new memory for me, which will be able to understand something from my past. So here it's more or less, like I said, it's a part of LSTM itself, but what people thought that, okay, fine. So maybe we can try to optimize a memory part instead of creating one more cell or one more state over here. Let's try to collapse it and then try to build a new network, and which people have named as a GRU. Simple. So again, GRU, you can try to use it for a machine translation, for a chatbot application, a stock price prediction, or wherever you can use LSTM, you will be able to use even a GRU. The only difference will be the time complexity for this particular training or for a prediction will be less as compared to the LSTM model that we are talking about. Apart from that, you will not be able to find much of differences between this GRU and LSTM, because we are just collapsing two or more gate over here, and we are trying to create one gate only. Now, so this is just an extension of LSTM. Now coming to the next. So we are able to understand this GRU, we are able to understand this LSTM. Now, we will be having a different kind of a problem in my hand. So what kind of a different problem that I will be solving with the help of all of these network, or like this kind of a neural network that we are talking about. So maybe we'll be solving a problem so where we can try to pass one single output, one single input will be receiving one single output. Maybe we can try to pass multiple output, single input, or something like that if we are trying to solve. So where I will be having a one input, multiple output, multiple input, multiple output, one input, multiple output. So means one to one, one to many, many to one, and many to many kind of a problem. There is a possibility that that will be in my hand, and I'll have to solve all of those problems. And this is where we can try to talk about maybe a different kind of a systems, or maybe a combination. So where I can try to combine, or we can try to stack this entire LSTM, we can try to stack this entire GRU in a different way, and it is going to solve a different kind of a problems. Maybe a one-to-one problems, one-to-many problems, many-to-one problems, or one-to-many problems. Now here, this is where you will be able to find out a bi LSTM. You will be able to find out a stack LSTM. So let's talk about basically a type of recurrent neural network that I will be able to build, and with respect to the problems, right? So let's suppose if I'm trying to solve a sentiment analysis problem. Let's suppose if I'm trying to solve sentiment analysis problem. So can I say that sentiment analysis problem is basically a many to one problem? So we are going to pass one long sentence, and then it is going to give me one single output. Means we are going to pass a multiple word or multiple tokens, and system is going to give me only one output. Can I say that, guys? Yeah. Can I say that, guys? Yeah. That we will be passing many inputs, means multiple words we are going to pass, and then ultimately we are going to receive only one output. So in this case, so when we have this sentiment analysis kind of a system we are trying to build, so obviously we are going to take one of these cell, maybe a LSTM or maybe a GRU or maybe a vanilla version of my RNN, and we have to stack it in a different way so that it will be able to solve a sentiment analysis problem. So let's suppose as a base model or as a base neural network architecture, I'm going to consider LSTM. So if I have to solve a sentiment analysis problem, so what I will do is, so maybe I can try to take a multiple combination of an LSTM, right? Multiple combination of an LSTM. So where it is going to take a multiple inputs, multiple input when I'm saying, I'm trying to say that a multiple word, right? So maybe X1, maybe X2, maybe X3 as a word I'm talking about this time. So I'm going to take a multiple inputs, and then I'm going to give only one output over here at time T. Now here, so I can try to use all of this LSTM. So LSTM one cell over here, LSTM another cell over here, LSTM another cell over here, LSTM another cell over here, and maybe we can try to combine. Maybe we can try to combine that. Okay, so this is how all of this cell is connected, and finally I'm able to get the output. So this is nothing but many to one kind of a architecture, or many to one kind of a structure. But again, my base model is going to be just a LSTM that I'm talking about, nothing else. Now there is a possibility that I will stuck up with a different kind of a problem. So maybe I stuck up with one to many kind of a problem. For example, a music generation, if I'm talking about. So maybe to generate a music, I can try to pass just one input that, okay, on this topic, try to generate a music for me. But if I'll talk about a music, so obviously the output is going to be multiple. Output is not going to be the like a single word or a single sentence. Output is going to be the multiple. So maybe we can try to like pass a input. Maybe we can try to pass a input. We can try to stack our LSTM maybe in this way. So we can try to pass only one input, and then our multiple LSTM will be connected to each other, and then every LSTM is trying to give me output. So 1, then 2, then 3, then 4, and then 5, and so on. So maybe I can have this kind of a combination as well. So where I can try to use a multiple cell of LSTM, then again LSTM over here, and then LSTM over here. Now there is a possibility that I will stuck with the many to many problem statement. Now what is that? So whenever we try to do a word translation, let's suppose if I'm trying to translate from Hindi to English, English to Hindi, Hindi to French, or English to French, English to Spanish, something like that. So obviously we are going to enter the sentence, a multiple words we are going to input, and technically we will be looking for a multiple output. So in that situation, again, maybe I can try to stack this kind of a LSTM in this particular fashion. All of the cell of the LSTM. So where all of this LSTM network will be able to take a input. So maybe X1, X2, X3, X4, X5. Obviously it is going to pass the share the state, and then it is going to give me the output. It is going to give me output over here. So this is something called as many to many system. So where like language translation is nothing but it's technically a many to many kind of a system. Maybe I will be having a bi-directional LSTM. So where both based on the past and based on the future, I will have to do a prediction. For example, if I am trying to solve a problem like a name entity recognition, any kind of a problem. So I will be having a bi-directional LSTM. Again, it's a stacking of the different set of the data. Maybe I'll be talking about a stack LSTM. So LSTM on top of LSTM on top of LSTM on top of LSTM. So layer by layer. So likewise, let's suppose we have this layer 1. On top of this, again, I'm going to create layer 2. Again, I'm going to create a layer 3. Again, I'm going to create a layer 4. In this way, my entire network will be much more complex, and it will be able to solve a much more complex problem statement. So it's just about a stacking or maybe a sequencing of any of this base RNN, which I'm trying to call as a vanilla RNN, or maybe a GRU, or maybe a LSTM. And yes, I will be able to solve a different kind of a problem in that context. So this is how you will be able to understand, like we try to solve our problems, but at the end of the day, our base model is not going to change. Our base model is always going to be same. So either it's going to be a vanilla RNN, either it is going to be a LSTM, or it is going to be a recurrent, so it is going to be a GRU, a gated recurrent unit at the end of the day. So making sense, guys, to all of us? Yeah. So technically whenever we try to do a coding, so again, we try to do the same thing, right? That in a one sequence, how many LSTM we are supposed to put up. Stack wise, if we are trying to create the stack, so again, how many layers we are supposed to create, in which layer, so what is the total number of the LSTM, base LSTM we are going to keep, or what is the total number of the base GRU that we are going to keep, or base RNN that we are going to keep. Now, so this story is fine. We have started our story from RNN, then we move to LSTM. So LSTM is better than obviously my RNN system or vanilla system, because it is able to memorize something. Then we move forward towards a GRU. So which is technically better than a LSTM, because instead of dealing with 2 gates or 2 neural network, so I'm just dealing with only, so instead of dealing with 3, so I'm just dealing with the 2 in case of a GRU. So this is completely fine. But, so again, this network will be having a problem. This network that we are talking about as of now, so this network was having a problem. So whenever we are talking about a very huge amount of a data, very huge sequences, or whenever we are talking about accurate prediction or accurate data generation, this model will not be able to do it. This model will not be able to learn it. So keeping that in a mind, so people have started thinking about something different, that okay, so maybe I can try to create some different kind of a network which is going to understand not just a single individual entity or a input, because all of these networks are going to take one single input individually, and then inside a network it will be able to, it will try to understand, not able to, so I'll say it will try to understand that, okay, what is a relationship in between all of these data, but it will not be able to retain much of a relationship. It will not be able to focus on one single word which is maybe connected with the past. For example, so if I'm going to say one sentence that Sudhanshu is a mentor, he is taking a class for a data science. Bappy is also a mentor. Bappy used to take a classes even for a generative AI and a data science, but the previous mentor is always, or the previous mentor is also taking a classes for a big data. So here I have used a word previous. Now previous is like very, very far from the initial line which I said that Sudhanshu is a mentor who is taking classes for the data science. So maybe it will not be able to relate that word previous with my sentence which I have said in a very, very beginning. Maybe this long sentence it will not be able to interpret. Maybe it will not be able to focus on a word previous. And likewise, there can be millions of different kind of a context. So where you are not taking a name directly, so like Sudhanshu or Bappy everywhere, where you are not trying to derive a relationship directly, because as a human being we all will be able to understand those phrases, but for machine it is supposed to focus on each and every word. It is supposed to focus on each and every token, and then it is supposed to find out a relationship between the past token and the next token, and based on that it is supposed to generate the new token, even for a long format of the sentences. Now, so LSTM or RNN, or maybe I can say a GRU, was able to solve a basic problem, just a basic problem, but these models was not at all good, or I would say very, very good with respect to solving a very, very complex problem for a very, very long sentences, or whatever problem that we have discussed in this particular place. So maybe for a sentiment analysis, maybe for a machine translation, even for a chatbots, even for a stock market prediction, weather forecasting, or maybe like a Siri or Alexa. So where we have a very, very long context. Now, so people have started thinking about a new kind of architecture, so which will be able to solve this kind of a problem in a easiest possible way. And this is where, right? This is where Google has published a new research paper called as Attention is All You Need, that we are going to discuss today. That is the main agenda for this particular class, I would say. Attention is All You Need research paper. So here you will be able to find out this official research paper. Attention is All You Need. So here, view PDF. No, this is the new one published in 2023. No, I'm looking for a 2018 research paper actually. But yeah, so attention formula is exact same, so it has not changed. So that's completely fine. Okay, so this is where this attention is all you need, which we are going to study. Now, so this paper was released in 2018. So this is not the original version of it. Maybe I'll have to find out the original version. 2018 PDF. 2018. No, it's the same one. Maybe I'll have to search a little bit, and then only July 23, Monday 2017. So V1 and V1. Let me view the PDF. Okay, 2017. Fine. So 2017, 2018 was the date. I remember basically 2018, but yeah, 2017 was the very first one, V1, and then 2017, then again 2017, 17, 17. So they have released this one 4 times with a different version. So fine. In any paper, you will be able to find out the exact same thing. Now here, so people was trying to propose one new architecture, so which will be able to understand even a long format of the context in a better way. That's a problem number 1. The problem number 2 is that it will be able to focus on each and every word. whatever word which is given, and it will be able to check the relevancy between each and every word to each and every word. It simply means that it will be able to give a attention on one single word, and based on those attention it will try to predict the new one. Means it will be able to understand, like, okay, so if there is a previous, which I have already taken as an example. So when I was trying to phrase a sentence, this Dansu is a mentor, and then Bappy is also a mentor, and then the previous one also takes classes for a big data and data science. This is the sentence which I have framed. So if I have to focus on one of the single word, so obviously this kind of a model will be able to focus in a easiest possible way. Apart from this, so this kind of a model solves one more problems. One problem, so what is that problem? So basically, if I'll talk about this RNN LSTM kind of a system. So this LSTM or maybe a RNN based system, maybe a GRU, it will not be able to understand the sequencing, that after which word is coming into a picture. This is again a second problem. So it will not be able to understand that what will come after what. So grammatical things it will not be able to understand in a better way. Context it will not be able to understand in a better way. So that is another problem. So obviously it will not be able to focus on a word with respect to all the other word, because it will always try to generalize. It will always try to generalize the entire phrases or sentence or the inputs. The second problem is, so first problem is obviously the attention part. The second problem is that which one will come after what. Again, it will not be able to understand, because it will always go ahead with the generalization. Now, so if I'll talk about this research paper, so this research paper is able to solve all of these problems. The third problem, if I'll talk about, so the third problem was that here in case of LSTM, so it takes 1 1 1 1 1 1 inputs. So again, these inputs will not be interdependent between each other. But here, so if I'll talk about this one, so it's basically a multi-headed attention. So it always try to even correlate, or it will be able to find out some sort of a relationship between all of those inputs. So now let's talk about this final version of this particular model. And then once you will be able to understand this, I'm going to show you this diagram. So again, in my yesterday's class, I have given you this particular link, right? On my studies class, I have given you this particular link. Now, in this particular link, if you are going to click on this Nano GPT, you will be able to see a lot of layers. There is something called as KQV, so query and then key and then values. There is something called as weight vector for this one. There is something called as layer normalization over here. You will be able to find out. Then there is something called as a feed forward network. You will be able to see. So there are so many things that you will be able to see in this particular architecture if you are going to zoom in this particular architecture a little bit, right? If you are going to, but yeah, majority of you may be not able to understand that what is the meaning of this head that we are talking about, head 1, head 2, and this is something called as multi-headed, right? Multi-headed. So what is the meaning of this entire multi-headed attention? Now, so what is a feed forward network that we are talking about? What is the KQV value that we are talking about? All of these things as of now, maybe you will not be able to understand, and how it is trying to learn, how it is trying to do a prediction. Although this is one of the amazing platform or one of the amazing place you all will be able to find out, which is explaining you each and everything in a detail. But to understand this, you must be aware about the algorithm. You must be aware about the architecture. Unless and until you are not aware about the algorithm or architecture, or I would say this entire one, you will not be able to understand this one. So one by one, let's try to decode this entire architecture, which is, that's the reason so I'm talking about the previous things, so that I will be able to build some sort of a context just to explain you this one, because this is the major part. And I'm going to spend almost more than 1.5 hour of time just to explain you this one, because there are a lot which goes inside this. And once you will be able to understand this, now if you are going to click on GPT-3, GPT-3 is nothing but it's a 96 such kind of a model. Simple. If you will talk about GPT-2, it's nothing but 48 such kind of a model. If you will talk about a GPT-4, it's nothing but 96 plus such kind of a layers. That's it. Like we talked about a LSTM, or like we talked about a GRU, right? Now when we are talking about one-to-one, one-to-many, many-to-many, many-to-one, right? It's nothing but we are just trying to stack it in a different way. We are just trying to combine it in a different way. That's it, right? This is what one-to-one, one-to-many, many-to-many, and many-to-one. And again, this is same. This is how we try to create even an encoder decoder. So encoder decoder is nothing but just one single box. So where we can try to pass our base models. That's it. This is something called as encoder decoder. Encoder decoder is nothing very different. Encoder means it will take all the inputs. Decoder means it will give you all the outputs. But yeah, it's kind of a boxes where so encoder decoder is not a particular architecture. Encoder decoder is technically a combination of all the base architecture or the base model. So encoder means responsible for taking all the inputs. Decoder simply means that responsible for giving you all the outputs. So here, right? So here, once you will be able to understand this entire architecture, technically this particular research paper, believe me, doesn't matter which model we are talking about, even a DeepSeek R1 or even a GPT-4, Cloud Sonnet, if we are talking about, or maybe a Llama with any billion parameter, you will be able to give an answer with respect to those model in a single line. Doesn't matter what people are going to ask you from the architecture side of it, you will be able to give all the answer. But to do that, you have to understand everything: input embedding, positional encoder, what is the meaning of multi-headed attention, adds a normalization, feed forward, again add normalization. Then inside a decoder side, so we have three layers basically. So one is a masked multi-headed attention, one is a multi-headed, and then we have a feed forward network, and it's taking input from the encoders basically. And here you will be able to find something called as NX and NX. So this is the main architecture which was released by Google in 2017, 2018, right? And based on this architecture, your entire LLM model that we try to discuss in today's environment is been designed. So this is the core building block of everything that we used to see in AI, or nowadays we are calling AI as a LLMs in general. So many people, which is not true. Obviously, AI is not just about the LLMs or not just about like generating some sort of a outcome. AI is way bigger than that. But yeah, so this is the most powerful system that we have seen so far, so forth. So as a layman, as a like a regular person or normal person, so I used to say that, okay, fine. So AI is all about LLM. But yeah, that's a different discussion. I'm not getting into that part. So shall we start, guys? Shall we start this discussion? Yeah. You have to focus for at least 1 hour or maybe little bit more than that to understand this entire architecture. But yeah, so once you are able to understand this architecture, believe me, for your entire life, doesn't matter in next 6 months or in next 6 years, what kind of a model is going to come up, you will be able to give explanation. And then I'll come to this visualization part as well. This is one of the beautiful one, but yeah, maybe as of now, you will not be able to understand, but after this discussion, you will be able to understand each and every layer and a meaning of all of these words that you are able to see, right? Meaning of all of these words you will be able to understand without even asking me or asking anyone. It's been almost 8 years since this, yes. And even like if you'll go and check my previous videos, right? So I have talked about this kind of this same architecture, I think 3 or 4 years back. There is a video available somewhere on YouTube. Okay, so let's get started, guys. So Kripa is saying that what about the semantics? What is the question, by the way? Yeah. What does it exactly means in this particular context? So basically, see, if I'll talk about a base model, right, LSTM or maybe a GRU, so it was good, but it was not that great in terms of understanding a semantics or syntactics with respect to a real data. But yeah, it was an initial version of it. It was able to solve a little problem, I would say, right? Little problem, not all the problems, but when I'm going to talk about this attention is all you need research paper, then you will be able to understand that yes, it is able to understand the semantics, it is able to retain the context, and based on that, it is able to provide the output. I have checked them, yes. Okay, so let's talk about it once again. Those who have seen my previous videos, so hopefully they will be able to understand. They are able to understand, but yeah, if you need a revision, so I think today is the class for the revision. I will go in a very step by step, guys, so that you all will be able to understand all of these things in a layer by layer fashion. And then we are going to refer a research paper as well. And then I'm going to show you that yes, now you all are able to understand research paper. This function looks a little bit scary, this function, but this is a main function. This is the function responsible for this entire architecture. And obviously after this class, we will be able to understand this particular function in a easiest possible way without even remembering a single term out of this one. Okay. So fine. Means technically you will be able to understand the entire research paper. So after this class, if you will go through and read out this entire research paper, you will not feel any kind of a pain. This is what I'm trying to say. Right. Okay. So this is I'll try to open up this architecture. So this is my architecture and I have to explain you this particular architecture. Okay. So like I said that there was a lot of problems. There was a lot of problems in terms of, I would say, LSTM or GRU. So even though we are going to combine into a different fashion, so maybe as a by LSTM, maybe as a in a sequential way we can try to combine, maybe in a stacked way we can try to combine, maybe we can try to build a many to many, many to one, one to many, many to many, anything, right? Any of these combination we can try to do, and then we can try to solve a complex problem. But still it will not be able to solve all of these problems, because at the one point of a time, so we are trying to pass only one data. That's a very first problem. So we are not talking about the parallelization over there. Second thing is, like, it will not be able to focus on one single word and its relevance with respect to other words, which is called as technically attention. So it will not be able to close, because if I'll talk about maybe a bank, right? So maybe I'm going towards a river bank, and I'm going to a bank. So again, bank means, so in one of the context, bank means what? So in one of the context, bank technically means that I'm talking about the bank of river, right? Bank of river, or I'm talking about something, a river basically. In context of river, I'm talking about the bank. And the other bank means, so maybe I'm talking about some of the financial organization, but bank and bank. So both of these words will be same, and it will not be able to find out the relevancy much. And even embedding wise, so any old legacy embedder, if you're trying to use maybe a word to vector, maybe TF-IDF, so it is going to give you the similar kind of a embedding for both the banks, because it never understands that what is a context of a bank in one manner and then in other manner. So there are a lot of problems, and this is where this entire transformer architecture, or this is something called as transformer, comes into a picture. So where it will be able to solve all the problems. So let me write it down over here. We are going to talk about a research paper called as Attention is All You Need. And this is true even for you. So you have to give a little bit of attention. So attention is the only thing that you need to understand this entire architecture. Okay. Now, so if you'll go and follow a blog written by GLMAR, so again, he has broken down this entire concept in a phenomenal way. In a oversimplistic way, he has broken down this entire architecture. And again, so it's very easy for anyone to understand what he has written inside his blog. And if someone is going through the concept, and I think this is the only one person on this planet so who has simplified this entire research paper. So even when I was trying to learn this entire things 5 year back, or maybe more than that. So even I have followed his research paper, I think 4 year back, I believe. I don't remember the exact year, but yeah, 4 year back. And based on his article, his entire blog. So I'm going to explain you. Plus, I'm going to take a reference from a research paper, the original one, and I'm going to explain you this entire things. Okay. So here, when we talk about this entire architecture, so you will be able to find out a couple of components in this architecture. So we are trying to take our inputs, right? We are trying to take our inputs. Let's suppose I'm trying to give our inputs. My name is SUDH. Now this is the input which I'm trying to give, let's suppose. So obviously this will go as an input in this particular layer. Then here, so people or researchers have introduced something called as input embeddings. Input embeddings is what? So I'm trying to give input into UTF-8, or maybe in English, I'm trying to give an input. Now system will not be able to understand this input as it is. So what we have to do is, so we have to convert this entire input. So this particular word, this particular word, this particular word, this particular word, or let's suppose if I'm given full stop over here. So this entire things into its numerical representation, or I can say into a vector space, it has to convert it, right? In a vector, it is supposed to convert it. So this is where this input embedding comes into a picture. Maybe I will be able to use a word to vector, right? So word to vector is a neural network based pre-trained model. So for each and every word, it is going to give you some sort of a embeddings. Embedding means a kind of a array it is going to give you. This is the meaning of a embedding technically, right? In a technical manner. So for my, let's suppose this is the embedding it is going to give me, and it is taking maybe 5 spaces. Depends. So I'm going to define maybe for 5 space, for 500 space, for 5000 space, depends, right? So what is the size of the vector which I'm going to consider? So here, the very first part is, so whatever input system is trying to take, so just try to convert this entire input into its equivalent vector. I can try to use even TF-IDF, that's completely fine, right? Or I can try to use a word to vector. And likewise, we have so many other different kind of embedding models or embedding technique which is available. Embedding simply means that, in a layman way, that we are trying to convert our data into its numerical vector representation. Vector means array. Into a multiple dimension we are trying to represent. Okay. Now here we are trying to use plus sign. So what we are trying to add over here? So there is something called as positional encoding. Now, even in case of RNN LSTM, the model that we have discussed just now, whenever we are going to pass our input, obviously we'll try to process the same thing. Means we'll try to convert our entire data into an embeddings, and then we are going to pass those data. It's not like I'm going to just pass like a my name is SUDH or full stop. No, I'll try to convert. So this is basically a common things, or this is basically a neutral thing with everything, whatever data you are going to pass inside the model, whether it's a text, whether it's a speech, whether it's a audio, video, or maybe a images, or maybe a continuous data every time. So you will try to convert those data set into its numerical representation. Now, so here we have a plus sign, and there is something called as positional encoding. So we try to do a little bit of math over here. So whenever we try to create this vector, or embeddings, whenever we try to create, so what we do is, so we try to add its position. So let's suppose if I have 4 words, or maybe a 5 word, technically here I have 5 words. So I'll try to create a positional encoding, and I'll try to maybe like give a positions or vector I'll try to create just for the position. So which will be able to identify that, okay, so my came into a first place. After that, name came into a picture. After that, is came into a picture. After that, SUDH comes into a picture. And after that, this dot comes into a picture. Now, even this part was missing inside RNN, because there was no positional encoding concept, which we have seen in case of RNN models, whether it's a LSTM, vanilla, or maybe a GRU that we are talking about. So here, it will try to add 2 things. One is an input and converts it into a embeddings. And then there is something called as positional encoding. I'm going to introduce a formula as well very soon. Just give me some time. So I will tell you that what is the actual formula that has been used, what is the actual mathematics which has been used for doing a positional encoding in general, right? Again, there are variety of ways by which I can do a positional encoding. At the end of the day, meaning of doing positional encoding is that it will be able to understand that what comes after what. Because as a human being, I understand noun, pronoun, verb, adjective, adverb, punctuation, grammars, all those things. But for machine, how it will be able to understand, right? Machine will not be able to understand that what will come after what. So it has to get something by which it will be able to build a relation, and it will be able to understand a grammar technically. So here, this positional encoding always helps us to establish a relationship between all of these words or all of these data that we are trying to pass. And whenever it will try to generate, obviously after training, so it is going to help us that, okay, so we know that what should come after what. We understand, my machine understands even a grammar. My machine even understands like where I should start, where I should end. So this is where positional encoding comes into a picture. And so we try to add input vector, which is called as embeddings. And then we try to add a positional encoding, which is again a vector, which is again an array. So we try to club it. And then what we do is, so we try to pass our entire data into this kind of a structure called as multi-headed attention. Now, I'll be talking about this multi-headed attention in a very depth, but hope we are clear about the input that we are trying to pass. Yes, guys, the input that we are trying to pass. Address to the word. Exactly. Technically, address to the word in a particular sentence. So hope it's clear that what kind of a input we are going to pass. So what kind of a input that we are trying to generate. So input wise, we are trying to generate a whole combination. So which is nothing but a combination of embedding plus positional encoding. So this is the input that we are trying to create over here. Okay, so once I will be able to create, then I have to talk about a multi-headed attention. So this entire data should go inside a multi-headed attention, and then over there it is supposed to perform some sort of a learning, or maybe I don't know what kind of operation it is going to perform. We'll try to explore, we'll try to understand. This is where the entire phenomena or the entire concept of this comes into a picture. So this is something that we are going to understand, because this is the core part. Apart from that, everything is like a very simple. So if I'll talk about maybe like a feed forward network, again it's a simple neural network. Addition normalization, again it's a very simple formula, but yeah, I'm going to explain you, I'm going to even give you a formula for this entire layer. So apart from this, everything is fine. Now, one more thing I would like to talk about before moving towards a multi-headed attention architecture, that we have one unit over here. This is one unit. This entire thing is one unit. And again, we have another unit over here. Now, this is basically encoder. And this is basically a decoder. So encoder means a module, a unit responsible for taking a input. Decoder means a model, a unit which will be responsible for giving me the output. Simple. In a layman way, the simple meaning of encoder is that a unit which will be responsible for taking a input. And then decoder means a unit which will be responsible for giving me the output. So this is one unit, and this is one unit representation. Here you will be able to see NX basically. So whenever I'm trying to create a model, so like I've shown you LSTM, so where we are trying to like build a different combination, many to one, one to many, stacked or by, something like that. So similarly here, so there is N. So maybe I will be having a multiple encoder stacked on top of each other, right? Multiple encoder. And then we will be having a multiple decoder unit. So where it will be getting an output from the encoder, the final encoder, right? And here it is going to give me the final output. So I'm just talking about this kind of a structure over here. But in this diagram, people are trying to represent, or researchers are trying to represent just one unit of a encoder and one unit of a decoder. And they have just given you the symbol over here, NX. Means it could be N, and this could be also N. Means there could be N number of layers, there could be N number of layers. Again, even with LSTM or even with RNN vanilla, or maybe even with the GRU, I can try to create maybe a multiple sequences, maybe into a stacked manner, maybe into a sequential manner, and I can try to keep it inside the encoder. And I can say that, okay, fine, this is my encoder. So inside one encoder, I can try to keep any base model basically. And then with permutation and combination, I can try to create any kind of a architecture. So encoder entity simply means that something is taking input out. Decoder means something is giving you the output. That's it. Okay. So now let's try to understand that we have a network, we have a particular unit, we are able to prepare the data. Now, how it is going to perform the computation, how it is going to perform the calculation at the end of the day. So here, on one side, so I'm just talking about a left-hand side architecture. So in left-hand side architecture, we are able to see, let me draw a perfect line. Okay. So here, so let's suppose I'm trying to give a input. So my input is nothing but combination of my current data and its positional encoding. So current data basically encoding and my positional encoding, which is going as an input. Now, so here this layer is something called as self attention layer. This particular layer is something called as self attention layer. So for example, if I have something like my name is SUDH. Let's suppose this is the data which I'm trying to give as an input. So what it will do is it is going to create a vector, right? It is going to create a vector for my, it is going to create a vector for name. It is going to create a vector for is. It is going to create a vector for SUDH. Vector is nothing but array representation of my data. So after doing this positional encoding and after doing this entire embeddings, after creating the embedding vector. So let's suppose these are the embedding vectors. I'm going to name it as X1, X2, X3 and X4. So these are the 4 data that we have. My name is SUDH. My name is Dhanshu. So this is my data that we have. Now it will go inside this self-attention layer, right? So it will go inside this. This is called as multi-headed. So this 4 data is going to go inside the self-attention layer, and then it is going to produce some sort of a output over here. So it is going to produce some sort of a output over here. Again into as a vector, it is going to produce some sort of a output for me. Some sort of a output for me. So let's suppose I'm naming it as a Z1, Z2, Z3 and Z4. And then this entire input is going to get into a feed forward neural network. So I will be having a neural network. So over here, I will be having neural network. Over here, I will be having a neural network. Over here, I will be having a neural network. And over here, I will be having a neural network. So it will go inside a neural network and then it is going to give me an output. So I have a multiple network, right? Feed forward for each and every attention that I'm able to get. So it is going to give me some sort of a output. Okay, that's completely fine. But what happens inside this attention? So how this attention is been calculated, because this is the main component, right? Apart from that, this feed-forward neural network is not a main component. We all understand that, okay, fine. So in a backward propagation, whatever data input it is taking, it will just try to learn. And then based on that, it will be able to generate some sort of a output. So this is a layer number 1. Now what we have to do is, so we have to basically break it down, this entire layer. We have to break it down into a small component so that I will be able to understand this entire self-attention mechanism, that how self-attention will be actually generated. So let's suppose, so here my name, right? Name is, so how this name will be able to generate attention for my is or Sudhanshu. How name will be able to understand that there is a name entity called as SUDH inside my entire input sentence that I have given, or maybe how is will be able to create its own attention and is will be able to correlate with my name SUDH. How is will be able to understand, or any of the words which is given over here. So how any of these words will be able to establish a relationship between each and every one. And this is where this attention mechanism comes into a picture. So now in a simple manner, I'm going to explain you each and everything, that how technically it is going to happen, how it is going to perform a calculation, and then how it is going to say that, okay, so I'm able to generate a relevance with respect to other word. Meaning of attention is generating a relations of one word with all the other word or all the other vector which is available inside my data set. So here there is a calculation which happens. So for example, I'm giving input. So let's suppose I'm trying to give input. My name is SUDH, obviously. So this is my X1, this is my X2, this is my X3, and this is my X4. This is my input. Now here, I'll try to create a embedding. Embedding is nothing but a kind of a array I will try to create for my input. So X1, X2, X3, and X4. I'm not talking about the size as of now, because size is basically a variable. So I can keep on changing those size, depends. And model to model, this is what people does. This is the hyperparameter, right? Now, inside this self-attention, so obviously embedding I'm trying to send. So inside this self-attention, the layer which I was trying to showcase, the self-attention layer. So what happens is, so people have designed a complete algorithm, so which goes inside this self-attention. So people said that okay, there are 3 parameters. So one is a queries, QUERIES. So one will be the query vector, one is a key vector, and one will be a value vector. So people said that okay, so when I'm trying to send this particular data inside my attention model, or this particular block, which I'm trying to call as a self-attention, when I'm going to send this data, so it is going to do a computation based on 3 things. One is a query, one is a key, and one is a value. So how it will be able to generate this query vector, how it is going to generate a key vector, and how it is going to generate a value vector, let's try to understand. So people said that okay, so for a queries, like to generate a queries vector, right? So maybe we can try to take one weight matrices over here. Maybe for a keys vector, I can try to take one weight matrices over here. Again, I'm not going after the size as of now, guys. So I'm just trying to explain you the entire phenomena. And people said that okay, so maybe we can try to name it as a weight for query. So weight for key and weight for value. So why it's a weight? Because the actual query vector is unknown to me. The actual key vector is unknown to me. The actual value vector is unknown to me. So basically these are the parameter, right? So I need something to train. I need something to adjust so that I will be able to understand the relation, right? I will be able to understand the relation. So here we are taking initially a random weight, a complete random weight. So we are taking this matrices. So query matrix, we are taking a key matrix and we are taking a value matrices. And based on that, I will be able to generate a query vector. I will be able to generate a query vector for all of my data. So for my x1, x2, x3, x4, for my name is Sudh. So I will try to generate basically a q1. I will try to generate q2. I will try to generate q3. I'll try to generate q4. So I will try to generate all of these query vector, which is nothing but again array, right? I will try to generate this query vector for this one. Now, similarly, how I will be able to generate this q1, q2? So simple, x1. So here, x1 dot product of wq, this one is going to give me q1. x2 dot product of wq is going to give me q2. x3 dot product of wq is going to give me q3. x4 dot product of wq is going to give me q4 basically. So data into this particular weight vector is going to give me a query vector. Simple. So data into a weight for a query is going to give me a query vector. Now, if I have to talk about a key vector, so similar thing is going to happen. So it is going to create a key vector. It is going to create a key vector. So key 1, key 2, key 3, key 4. How? So data, embeddings of that into weight for the key. Again, data, weight for the key. So K1, K2, K3, K4 it is going to create. So data into basically W of key, K. And it is going to get K1, K2, K3, K4 for X1, X2, X3, X4. Simple. So query vector. Even now, see guys, so these are the random vector that we are trying to create just with respect to my data, because this weight is initially a random data, a random weight which I'm trying to consider. So weight is basically what? It's a trainable parameter. So I'm trying to generate as many relation as possible. So I've just taken a weight over here. Now there is a value vector that it will be able to create. A value vector that it will be able to create. So basically V1, V2, V3 and V4. How do we be able to create? So again, data, I can say xi into weight of basically this V, and it will be able to create query keys and a value vector. Now, this is not a perfect vector as of now because I have to train it. I have to train all of these weight that I have taken, and then only I will be able to generate a perfect one. But here, so I'm able to generate a query keys and values. As of now, I'm not using it. I'm just generating it. Yeah. Now, what is my whole purpose? My whole purpose is to relate each and every data which is available inside my input. That's my whole purpose, right? So my whole purpose was to relate my with name, my with is, my with SUDH. Again, name with my, name with is, name with SUDH, is with my, is with name, is with SUDH, and SUDH with is, SUDH with name, SUDH with my. That's my whole purpose. That's the reason. So I'm trying to do something over here. I'm trying to design this entire architecture. I'm trying to learn this algorithm. So how I will be able to fulfill that particular purpose, right? Let's talk about that now. So here, once I will be having a query key and a value vector, then there is something called as a score, S-C-O-R-E, a score that we try to calculate. And here we try to establish a dependencies. Here we try to establish a dependencies, a relation between different word. So how do we try to establish this relation, or how do we try to do this kind of a calculation? Let's try to understand. So here the very first vector was a query vector, right? So query vector. So what we do is, so we try to multiply this query vector with a key vector. So here query 1 with key 1, we try to multiply. Again, so query 1 with key 1 and then key 2, right? A second data. Query 1 and then key 3. Query 1 and then key 4. Now, we are going to perform this operation just for what? So just to establish a relationship with my X1 data, with my first data, because from first data I have generated question queries, right? So with all the other data set, Q1, K1, Q1, K2, Q1, K3, Q1, K4 in this way. Now, similarly, I'll try to do it for X2. So for X2, how I will be able to do it? So Q2, K1, multiplication, Q2, K2, Q2, Q2, K3, Q2, K4. Similar. Then Q3, K1, Q3, K2, Q3, K4, Q3, okay, so 1, 2, and then 3, and then K4. And then Q4, K1, Q4, K2, Q4, K3, Q4, K4. So we will be able to generate this for first data, this for second data, this for third data, and this for the fourth data. I have in total 4 data. So X1, X2, X3, and X4. The whole purpose behind this one is to understand the relation, right? Understand the relation. So this is going to give you the score. This is nothing but just a multiplication of the vector, right? Queries vector and the keys vector. So here I'm able to establish a relationship between Q1 with everyone, Q2 with everyone, Q3 with everyone, Q4 with everyone. So this is just a random vector which I have taken, because at the end of the day, I will have to train this weight. And once I will start training the weight, it will start adjusting itself. It will start adjusting itself with respect to the relations. And eventually I will be able to build the perfect relation. So this is something called as a score. So I will be able to calculate all of this score. So in my situation, so here in total, I will be able to calculate 16 number of score, right? 16 combination I have, 16 number of score. So this 4 combination for 1, 4 combination for 1, this 4 combination for 1, and this is going to give me the score. Now, once I will be able to calculate the score, right? Once I will be able to calculate the score, then, right? Then what I have to do? So then I have to basically divide. So D-I-V-I-D-E. Divide by what? So divide by root of dimension. So dimension of basically a key vector. So let's suppose my dimension of my key vector is 25. So what is a root? What is the root of 25? It's going to be 5. Let's suppose it's going to be 100. So in that case, it is going to be 10, right? So whatever is a dimension of my key vector, so I'll try to divide dimension of keys. That's the reason. So I have written D of key, right? So I will try to divide all of these scores, which I'm able to find out, with basically a root of this dimension of key. So like I said, if dimension of this key is 100, and again, these are the adjustable parameter. That's the reason. So I'm not taking a perfect number over here. Let's suppose if I'll be talking about a BERT, if I'm going to talk about distal BERT, if I'm going to talk about ELMO, if I'll talk about T5, which is again, all of these models are basically a transformer based model. So again, these all dimensions are going to change. This is just a hyperparameter, right? We change it, we name the different model, because maybe that model is going to work for some of the specific task basically. So here, what we do is, so we are going to divide this Q1, K1 with root of D of K, this again with root of D of K, this with root of D of K, with dimension of K, right? Similarly, so with all, so we are going to perform this operation. We are going to perform this entire operation. Now, once I will be able to perform this divide operation, and then I will be able to get some sort of a data, right? I will be able to get some sort of a data. Let's suppose I'm getting 100 over here, and then I'm getting okay, so let's suppose 20 I'm getting over here. Let's suppose a 40 I'm getting over here. And let's suppose 22 I'm getting over here for one of the instances for my one data, which is X1, because I am dividing all of these four. So 1, 2, 3, 4, 4 such kind of a things I will be able to generate only for one data. So for another again 4, again 4, again 4, right? So I will try to perform this operation, divide by dimension of a key matrix or key vector. Then I will try to find out what? I will try to find out the softmax. I'll try to find out the softmax. And we all know that softmax is nothing but a probability function, right? Softmax is basically a probability function. So it will always try to give you the probability, that what is a probability that this word, let's suppose we have what we have done over here. Just try to again reiterate, right? Just recall this particular one. So what we have done over here, so we have established some sort of a relationship with one data with others, right? This is where we have written Q1, K1, Q1, Q1, K2, Q1, K3, Q1, K4. So this is something that we have established. Now, if we are trying to find out the softmax, means a probability, right? So what kind of a probability it is going to give me? So it is going to give me a probability. So which one will be having the highest probability? So it is going to give me a probability that, okay, so which one is more related? Let's suppose if a score is 100 for this one. So obviously probability for this one is very high. It simply means that one with one means word one with one relation is very high. If let's suppose if this one is giving me the highest probability, it simply means what? That word one is very much related with the third word, right? Very much related with the third word. So word will be having a relationship with itself. Word will be having a relationship with others as well, right? So this softmax is ultimately going to give you the probability, and this probability is going to tell you that, okay, so how much related we are. So maybe with respect to like a 20% probability we have, maybe 80% for someone, maybe 2020, like 20, and then 60 probability that 40 probability that we have. So this is going to eventually give you a probability. Simple. So once you will be able to get the probability, so now you know that, okay, so which depends upon what more, and which depends upon what in a less way. So which word or which token or which embeddings depends upon what more and less. This is something Softmax is going to give it to you. And in this place, you will be able to create a little bit of attention. Means you will be able to focus that, okay, fine. So this is more related to this one. Similarly, so for Q2, for second input, you will be able to do the same thing. For third, you will be able to do the same thing. For fourth, you will be able to do the same thing. Means from everyone, right, from all of this 16 combination, which is technically for a 4 inputs, you will be able to find out a maximum probability over here. Yes, maximum probability. Agree, guys, everyone? How to get a dimension of the key? Like I said in a beginning itself. So even if you will go through a research paper, so people have, I'll show you the dimension actually. So what dimension that they have taken, and even if you will follow the GL bar blog, so he has technically taken one of the dimension, but I'm not taking a dimension over here or particular dimension. The reason is very simple. I could have taken a 512 dimension. I could have taken any other dimensions over here, and based on that, I could have shown you these things, but it is a hyperparameter. Simple. It's a hyperparameter. It simply means that it's under my control. Yep. That's the reason. So I'm not talking about dimension. I have clearly mentioned that I'll be talking about it once I'll finish this one. Yep. But it's a hyperparameter. So I'm not talking about dimension of anything as of now. What I'm trying to explain you over here is the story, right? The story that when I'm saying, because what is the purpose behind discussing this entire attention is all you need, so that I will be able to understand that how system is understanding that where I have to focus less, where I have to focus more. That's the whole idea, right? That was a problem with my previous model, right? That was a problem with my LSTM. That was a problem with my GRU or RNN or any variant of RNNs, right? So here we are trying to understand the story line, basically the entire storyline step by step, that how the system is trying to understand the relationship in a better way as compared to the previous one. The previous one was very flat, right? So previous one, simple. So now here we are going to calculate this probability. So Softmax is going to give you technically a probability. So we have already used query and key, right? We have already used query and key over here. Then what we are going to do is, so let's suppose if it is able to calculate a softmax, maybe I'm going to like give a probability over here as maybe like a 40 and then like a 20 and then maybe like a 25 over here. What is the total math? And maybe let's suppose 15, although it's not correct, but I have just taken the one simple number over here that, okay, 40% probability, 20%, 25%, and then 15% probability. Total is 100. I have taken a random one, guys. Again, no calculation as of now I'm doing, means no calculation. So once I will be able to calculate this, let's suppose, then what I'm going to do? So I'm going to do the next step. So here, softmax into value. So I had a value vector, I haven't used it, right? I have already used key value. I have already used a query vector. So here, softmax into a value vector. And then we are going to generate basically a value vector. So we are going to multiply this probability with a V1, V2, V3, and V4 technically. And we are going to just do the multiplication. This into this, this into this, this into this, this into this, this into this. And again, this value vector is a trainable vector, right? Because we are able to generate from where? From the weight of V. So it's a trainable parameter basically. We can try to train it. It will be able to learn the relation. And then once I will be able to do that, so then we are going to perform the summation operation of V1 plus V2 plus V3 plus V4. Similarly, I will be doing this. This is for my input X1. Similarly, I will be doing for X2. Similarly, I will be doing for X3. Similarly, I will be doing for a X4. So I will be able to create one long concatenated matrices based on the input which I will be able to get. So here X1, and it now understands a relationship with all the other one. X2 value vector or summation of the value vector is going to understand its relation with all the other word. X3 again, it will be able to understand its relation with all the other one. X4 will be able to understand its own relation with all the other one. And that was the whole purpose, right? So that everyone will be able to understand a relationship with everyone else. So here we are going to create this one. Fine. So we are going to technically, right? We are going to technically perform this entire summation operation, and then we are going to like get the summation. And let's get back to my research paper now. So here, right here, you will be able to see a function, right? You will be able to see a function. Now let's try to interpret this function, guys. So here initially what we have done, query vector into key of tth, right? Key of data, tth data, right? We have done, this is what we have done initially, if you remember. Then we have divided it by what? A dimension of a query vector, root of dk. This is what I have written. Then we have passed this data into what? Into a softmax to find out what? To find out the probability. And then we have multiplied this probability term with what? A value vector, right? Value vector. And this entire thing is going to give me what? A attention. Can I say that an equation which was written inside a research paper, I'm able to understand, I'm able to decode? Yes. So combining this is going to give me a attention. Can I say that now I'm able to understand this main equation, the equation which was responsible for like a attention? Yes, everyone? Can I make a statement? Yes, right? So now if you will go back and look into the original research paper, you will be able to understand it now that this equation will not look alien to you, right? This equation is pretty much understandable and it's pretty much decodable. So we all can understand this equation, and whatever in a step-by-step manner, which I have explained you. Now, if you will start reading out this one, you will be able to find out the exact same thing. You will be able to find out the exact same thing, right? Now, Rohan is saying relationship between was this equation helps us give the attention. Exactly, right? Exactly. Now, we are able to understand till this particular part. We are able to understand this one. Now, so here, if you will look into this research paper, right, here you will be, if you will look into this one. So it's called as multi-headed attention, multi-head attention. Now, what is the meaning of multi? So now we are able to understand what is the meaning of attention. Yep. We are able to understand that, okay, fine. So what is the meaning of the attention? Now, what is a meaning of a multi-headed attention? It's very simple. Anyone guys who can guess what is the meaning of multi-headed attention, by the way? Attention we are able to understand. What is the meaning of multi-head? Yep. Anyone? Waiting for your answer, guys. Okay, so Amrendra is saying multi-layer, multi-QKV. Amrendra, you are incorrect. Sai, you are correct. So multi-headed, right? With respect to each other. Yes, Masood. So here, attention we are able to understand. Just from there, just try to derive it. What is attention? What is a multi-headed? So see, we all understand attention, right? Attention means what? So when I said attention, so I have simply shown you with respect to x1, right? With respect to x1. Now this is one attention, right? Let's suppose I'm going to name it as a Z1. Fine. Now, even for this, I will try to do the calculation. Even for this, I will try to do the calculation. Even for this, I will try to do the calculation. I'll try to do the calculation. Now, so this is head number 1. This is head number 2. This is head number 3. This is head number 4. So can I say it's a multi-headed? Yes, it's a multi-headed, right? So in this way, we are trying to achieve what? We are trying to achieve basically a parallelization. So if I'm going to combine H1 plus H2 plus H3 plus H4, and if I'm going to train my model, can I say that I will be able to involve a parallelization into my model training, right? Parallelization. Whereas if I'll talk about a LSTM, it was 1 to 1. So one data it will take at a time, then second, then third, then fourth, then fifth, and so on. Then it will be able to understand. But here, so I can say that yes, I'm able to achieve a parallelization with the help of multi-headed. And this is what the symbol represents, right? That we are getting a data here, then 3 data. 3 is going, right? 3 different is going. Now that can be 30, maybe 40, 400, 4000, right? Depends, right? This is what we try to call as a input token, output token, by the way, with respect to ChatGPT or any other like a LLM model that you are using nowadays, right? So input token, output token. So here multi-headed, so obviously it will be able to understand, or it will be able to achieve the parallelism in between, just with the help of this multi-headed attention. So now we all know that what happens over here. Simple, the equation that we have discussed and combination of all. So that's called as multi-headed, right? So try to find out the attention of each and every word, and then with everyone, and then combine it. Combine each and every one, like I have mentioned over here. So just try to combine basically H1, H2, H3, H4. H1 is coming from X1, H2 is coming from X2, X3, and so on. So combine it and then try to send it. Sir, what was the original blog you referred to? What was the original blog? No, like this is the original research paper. So whatever anyone is trying to learn, everyone, this is the source of everything, right? This is the source of everything. Fine. So here we are going to combine all of these attentions, and then we are going to build a big one. Now this big one, right? This big one which I'm talking about, which is a combination of H1, H2, H3, and H4. So this entire matrix will go inside my network, and which will be able to eventually understand that, okay, fine. So like what and how it is trying to train itself. Simple, right? Then what we have. So then in my next layer, if I'll talk about my next layer here, so we have basically addition and normalization. So anyone who can explain me addition, I think it's simplifying, right? So addition is simple add operation. Then there is something called as normalization. So anyone who can explain me like what is the meaning of normalization? I believe it's coming from the statistical concept. It's coming from the statistics. So anyone who can recall the normalization. Recently, I think I have already talked about this normalization in my machine learning class, I believe. Yep. So anyone who can tell me what is normalization, by the way? Stabilizing the input. Okay. So Sai is saying data minus U by standard deviation. Actually, Sai is correct again. Once again, he is correct. See, guys, in normalization, what we try to do. So we try to like place a data, or we try to shift a data in such a way that it will try to like give you mu is equal to 0, standard deviation is equal to 1. This is what is called as normalization, right? And at the end of the day, we are dealing with the vectors. Technically, it's a numerical value that we are dealing with. That's so same the concept, the fundamentals that we try to study in case of statistics, same thing is applicable even over here. So in case of normalization, what we try to do, so we try to find out the mu is nothing but a mean. Then we try to find out the standard deviation. So we all know, so what is the formula for standard deviation? So 1 by n, and then summation of data minus its mu square is called a standard deviation. And then 1 by n summation of all the data divided by like total data is something called as mu. And then if I have to normalize the feature, so normalize feature, let's suppose I'm trying to say x delta over here is nothing but original data minus mu divided by root of this plus epsilon. So this is a new term which has been introduced over here just to deal with a little bit of error or to tune it. So here, this is something called as a normalization in general. Very simple, right? This is something called as, so basically this eta which I have written over here, so it's nothing but it's a constant which has been used for a stability. That's it. So this is just one of the factor that has been used over here, which is going to give you a stability. And then there is something called as linearly separable parameter. So basically a learnable parameter which people have introduced inside this one while doing addition normalization. So this is something called as, let's suppose if I have to generate the data, so this is called as like a gamma, and then this normalized data x of delta plus beta. So here this gamma which I'm talking about, so it allows the model to scale the feature, basically scale whatever data that we are getting from this attention, scale the feature. And the beta which I'm talking about, so it's nothing but it allow the shifting of the data if it is necessary. So this is the final addition and normalization. This is what happens in case of addition and normalization. So we have introduced 3 parameters, so gamma, beta, and this eta parameter. So eta is nothing but just for like adding a constant to create the entire stable data over here, and this eta and then beta that we are talking, gamma and the beta that we are talking about. So gamma is for feature scaling, and then beta is for shifting the data. As you can see, we are adding it, right? We are adding it. So this is what happens with respect to all the data that we get from the multi-headed attention. The previous matrices which I have shown you, which is a combination of all the head, right? Which is a combination of all the head. Now, once we are able to get a data in this particular layer, right? Once we are able to get the data in this particular layer, then what do we do? So then we send this data, right? Let's suppose we are getting a data, then we send this data into a neural network. This is a feed forward neural network actually. Simple neural network. So there will be an input layer. Input will be this one, right? The arrow that I'm trying to show you. And then there will be the output layer. In between, there will be the hidden layer. Again, depends how I'm trying to train my model, and accordingly, so I'll try to take the hidden layer. I'll try to take maybe like a functions inside the hidden layers, and the output functions on all those things I'll try to consider. The normal neural network that we try to build, the way we try to build it. So similarly, we try to consider over here. Now, this is going to combine. This is going to create basically encoder. This is what happens inside the encoder. Now, let's try to understand this particular part. Now here, you will be able to find out something similar. So inside a decoder, again, we are trying to pass the output embedding. So let's suppose we are trying to build a model for a translation or maybe for a data generation. So let's suppose if I'm saying that my name is SUDH and I'm trying to do a translation. Maybe my name is SUDH into its English translation. So my English translation will be Mera Naam Tanshu hai. This is going to be my English translation, right? English, Hindi English, right? English translation. Let's suppose I'm trying to do something like this. So this will go here. And again, so I have to train my model. I'm talking about the training phase of the model. So inside a training phase, I will try to basically pass this particular data, which will go inside my output phase. Again, same embedding, positional encoding will happen. Then it will go inside a multi-headed attention, but here people have mentioned masked multi-headed attention. So here we try to perform everything that we have done in this particular layer into a multi-headed attention layer. But here we are trying to use masked. What is the meaning of masking, by the way? Again, meaning wise, it's very simple. So meaning of this masking is that whenever I'm trying to send this entire data, I will try to hide this data. I'll try to keep that as a question mark so that my system will try to predict that, okay, so after this Mera, what will come here? And then before this, what will come? Then I will hide this one. So randomly, I'll keep on hiding one and another or certain percentage of the data, and that is called as masked multi-headed attention. Rest of the calculation is exact same that we have seen, like a query key and a value parameter. With respect to query key and value, whatever we have seen, it's going to be exactly same. The only thing is we are going to mask some of the data so that my model will be able to learn and understand in a better way. So this is something which goes over here. So we are trying to give a output data, the expected one. So we can say a Y data. So here we have a X data and here we have a Y data set. At the time of training, we are trying to give. Here we are masking, again addition normalization, same step that we have performed over here. It will go over here, right? It's a multi-headed. It simply means that a multiple input we are trying to pass to achieve the parallelism. Now it is going to learn from the expected data. This entire layer is going to learn from the expected data. Now here, again, we have another layer, as you can see. Now in this particular layer, right, in this particular layer, you will be able to find out that we are getting output of encoder into this one, output of encoder into this one, plus from the learning of its own decoder layer with multi-headed, masked multi-headed attention. So it's going inside again one more multi-headed attention model. So this model is taking input from the encoder, which has taken the original input data, and it's taking an input even from the original output data. Means it will be training itself with input and output both, and it is trying to understand a relationship in between. Simple. And then we are sending this data again to the neural network, addition or normalization in this particular layer. Now moving ahead, so here we are trying to create a fully connected layer, and then finally we are trying to, like, depends upon the task which I'm trying to solve. So I'm trying to ask a softmax. I'm trying to create a softmax so that it will be able to generate a data with the probability. So whichever it will be having a more probability, that data it is going to generate for me. But yeah, this is the training architecture. Now, if I'll talk about a BERT, so BERT large, if I'll talk about, so in BERT large, you will be able to find out that we have 24. Sorry, my handwriting is not very great here. So in case of BERT large, if I'll talk about, so we had technically 24 such kind of a encoder layer connected with one after another. This layer I'm talking about. That's the reason it's given as N, because it depends upon me that what kind of a arrangement which I'm looking for. And then we were having 24 decoder layer, means this network we had 24. Forget about this and this, these two, right? This is like an external one. Depends upon my task, I can fine tune this one. I can try to change it. I can try to replace it. So we had basically 24 on a decoder side. 24 on a decoder side in a BERT large. If I'll talk about BERT small, so we have 12 on a encoder side and 12 on a decoder side. This is something this is the architecture that we are talking about basically in case of a BERT. Now I'm coming to this one. So here I'm going to show you first of all Nano GPT so that you all will be able to correlate. So again, guys, I'm pinging you this particular link. Even you can try to open up now inside your system, right? So that you will be able to experience it more and more. If you would like to go ahead with the calculation, so you can try to check over here that what is happening inside the embedding layer. So here this is one of the, like I said, one of the best over the internet you will be able to find out. So here, as you can see that input and output both is given. It simply means that X and Y, both the values are given. And just try to focus over here, guys. Believe me, your GPT or any GPT based model, any kind of a LLM that you know, now you will be able to correlate in an easiest possible way. So here, input and output, both the data will be given at the time of training, right? It will be converted into a tokens, right? It will be converted into a tokens. And now when we are trying to convert into a token, so basically it's a embeddings, right? It's a embedding in which we try to convert each and every one. So it's a embedding in which we try to convert each and every one at the end of the day. Fine. And then we try to add it with what? We try to add it with the, so token embedding plus positional embedding. It's going to create what? It's going to create basically input embedding, input data. Agree everyone? Yeah. So from where token embedding is coming, maybe some sort of a TF-IDF, some sort of a word-to-vec kind of a model we can try to use over here, and then we can try to create a token embedding. And then positional embedding, so like calculation, basically we try to like calculate with respect to cos and sine over here. And technically it's try to give you the position, right? It's number, it's an array, which is going to represent a particular position for a particular data, particular word into the entire sentences. So we are going to attach positional encoding and this one, and this is how you will be able to create the input embedding. As you can see, this arrow is flowing into two. So this is how I'm going to create the input embedding, which will be the input which will go inside my model. Now, once I will be able to create the input, then what? So now let's talk about this one. A little bit like hard to play with this, but yeah, it's fine. Slowly, I'm going to move. Yeah. So can I say that we are able to get this input? As you can see, this green line, right? This green line. So we are able to get this input, this entire input over here. And then we are trying to create this entire attention. So we have basically a weights. As you can see, we have a weights WQ, KQ, VQ, right? We have a weights. Again, we have a WQ, KQ, VQ, WQ, KQ, VQ. And then we have a vector, query vector, key vector, and a weight vector. So same thing that I have explained you from the beginning. That okay, so we are talking about self attention, data is gone. Then again we have a query, key and value, and then here we'll be having a WQ, KQ and VQ, which is a trainable parameter, right? So this is the trainable parameter that we have over here. So we are trying to pass it, and again the kind of a calculation which I have shown you. So based on that calculation, it is trying to give me the final outcome. As you can see, if you are going to follow the arrow, right? So on this layer normalization, right? Layer normalization, which is nothing but a data minus mu divided by root of sigma s square plus epsilon. And then we are trying to pass those things into another function. So where like we have a gamma into the normalized data plus beta, right? So here it is trying to perform a normalization. So just try to hover your mouse anywhere, and then it is trying to perform that operation. So once it is done, right? Once it is done, so attention residual, all of these things it is going to create. Little bit tough. Okay, now it's like flipped. Yeah. So I was talking about a multi-headed. If you are going to hover your mouse, you will be able to find out that there is a head 1, head 2, head 3 and head 4 with respect to all the words. This is what we have discussed, right? So head 1, head 2, head 3, head 4, it is going to create. And then finally, it is going to send this entire data into MLP, multi-layer perceptron, which is nothing but a feed forward network where it is going to send the data. Then again, so on a decoder side of it, right? So once encoding will be done, once this entire thing will be done, then on a decoder side of it, so it is going to perform all of these operations, with respect to my output data. And finally, let me call this final point. Yeah. So even you can try to play it, guys, one by one. If you are going to play it, then it is going to show you things in a better way, much better way, I would say. Yeah. So again, and then finally over here, you will be able to find out that we are trying to do some sort of a prediction over here with the help of Softmax function in this particular place, right? Sort of function. So now if you will just go through this entire architecture, you will be able to understand the actual reality that, okay, so how and whatever we have discussed, right, you will be able to understand in a easiest possible way. So just try to expand one by one, all of these layer by layer in the smoothest possible way. And then you will be able to understand. Now, if I'll talk about a GPT-3, right? Now, inside a GPT-3, right? Inside a GPT, sorry, like I'm not able to expand much. Just to show you. So this GPT-3, if you'll talk about, so we have 96 such kind of a stacking of same thing that we have discussed, same architecture that we have discussed. And if I'll talk about a GPT-4, so they have not revealed it, but yeah, so it's having 96 plus. If I'll talk about GPT-2, it's having 48, such kind of a stacking, such kind of a architecture, one on top of other, as you can see parallelly. So it's been stacked on top of each other in diagram. If we'll talk about this GPT small, so it's having almost 12 such kind of a stacking in its place. So, but yeah, the main architecture is this nano GPT. So where this person has explained each and everything, and he has created one of the amazing, I would say, a visualization. So really thanks to him, obviously. So we should always appreciate such kind of person who do this kind of things for the society. But now I believe we all are able to understand that what is attention is all you need, first part. Second part is, I believe we all are able to understand how GPT actually train itself. So yesterday I have already told you, I talked about a GPT flow, that okay, fine. So whenever I'm trying to train any kind of a model, so what are the steps that we are supposed to follow? I believe you all remember that what are the steps which is required. Now, today I have already discussed that what kind of a network where we try to send the data set and how this network is going to train itself. So hope we are able to connect my yesterday's class and we are able to connect my today's class. Making sense, guys? Your board diagram is more easy to understand. Yeah, obviously, like board diagram, that's the reason so I'm trying to draw the board diagram, right? Otherwise, I would have just shown you over here, but I know practically it's not possible. Just to get an experience. Again, this is not a perfect one, but yeah, just to get an experience, you can try to go and explore. I'm not saying that you will be able to learn anything. If you know things, then only it is going to help you out. Otherwise, it is not going to help you out. Simple. Yeah. Okay, so now I am done, I believe, with my today's class. Let me share this entire PDF. Attention is all you need. And I'm assuming that you all are able to understand this one as a story and in a sequence, that what was the problem with respect to our previous one, what kind of a problem that we are trying to solve with this particular model. And now if you will go and explore any model and every model which is available, whether it's a llama, whether it's a like a Cloud Sonnet model, or maybe it's a GPT model, GPT 4o, GPT 4o mini, or maybe O1 model, or maybe a DeepSeek, anyone, right? Anyone. Building block is a same thing. They have just changed the parameter, they have just changed the stacking, they have optimized somewhere, they have used some other functions in some other places. But if I'll talk about a design side of the model, it's absolutely same. So if you'll go to Google and try to search that, okay, fine, how many layers this model is having, what are changes which has been made. So in their research paper, you will be able to find out even those differences. Over there, you will not be able to find out this diagram because they are assuming that you are already aware about it. But yeah, on top of that, you will be able to learn that what they have manipulated or what they have changed, how they have stacked, how they have combined the entire things. And when I'm saying entire things, that thing is basically a thing that we have discussed in my today's class. Attention is all you need. Finally found out how to understand this weird diagram in the paper. Okay. Kripa is saying, in case of generation, what will be the output embedding? See, Rahul, so we are trying to create this output embedding when we are trying to train the model. I have mentioned clearly, right, that when we are trying to train it, so basically we are trying to do a supervised training, right? Supervised means I will be having a input data as well as I will be having the output data. Now, when I'm talking about a generation, right? Let's suppose I'm talking about the generation. For example, you're using ChatGPT. So you're trying to type something. ChatGPT is going to give you something, right? Over there, you are not training it. It means what? It means there won't be any output layer. There will be the decoder layer, encoder layer, pass the data, go through all the encoder, then the decoder network, and then finally on other side, if you remember, right? On other side, so we had a output layer. If you remember this one, where is the paper? Yeah. So we have this one, right? We have the output layer. So don't think that this is going to like give you. This is been used at the time of training because we are trying to perform a supervised training over here. Making sense? Okay, so I believe Rohan, you are able to get your answer. So normalization and standardization are often used interchangeably. So yeah, that's the reason. So I'm just using that term. Fine. Okay. Any other question, guys, for me? Anything? So hope all of you have liked this particular session. All of you are able to recall the concept, or those who have never understood this particular concept, now you will be able to understand. Yep, everyone. Yeah. So please try to give one or two posts on LinkedIn. That will be amazing if you're going to post it. Please give us a session based on transformer like this tomorrow. I can give you a session, but uh, on anything, I don't have any kind of issue. Again, so transformer, that's not going to be complex as we are able to understand this part. But this is your interview session, I believe, a bootcamp for interview. So generally, what I do is like I try to like discuss not all the topic in all the batches. I try to discuss a topic in a respective batch which is required in a particular, like, depends upon the requirement, like depends on the batch that we used to form. That's the reason. So we have multiple batches. We have FSDS batch. Obviously, over there, I'm not going to discuss anything with respect to just an interview. So I have to discuss everything from the scratch. So let's suppose if I have spent 2.5 hours over here, I'm going to spend even more and more hour in that batch just to explain the same concept. And I'll go even in deeper and deeper and deeper, right? So there is a purpose of all the batches. And again, with Euron Plus, you can feel free to join all the batches. You just have to spend your time. But again, believe me, it's going to be worth it. If you're able to understand everything inside the class, believe me, even for next 1 or 2 years, you will not have to look into anything. For any interview, you don't have to revise. Just go and attend it. You will be able to clear. By the way, sir, would you say being able to code the base GPT model from the scratch is important to understand this with perfection? Yes. Yeah. But again, so we no one codes this one. So basically, like we can just try to call the high level APIs and then we'll be able to build it. After that, we can solve the query questions by ourselves, please, sir. Okay, are you talking about the same one, transformer? Okay, fine, not an issue. I can discuss. So like discussing anything is not a big deal for me. Like just like okay, fine. Let's have a discussion then. Fine, just give me a reminder tomorrow so I can come inside the class and discuss about it. So fine guys, thank you so much for attending this 2 hour 45 minute of back-to-back continuous lecture, and hope all of you are able to understand. So with that, thank you so much. Expecting some of the posts from some of you. I know many of you are not going to post. Maybe you will feel shy, but yeah. So expecting some of the posts from some of you on a social media, so that other people will get to know that yes, this kind of a discussion is going on. With that, thank you so much, everyone. Have a good night. Let's discuss another topic in my tomorrow's class, same time, 9 p.m. IST. Thank you so much, everyone. Thanks. Take care.